Hey Lou, if it's okay for you now, it would be great if you could jump over to the Shadow of the Scientists Zoom link. That way you can share the JIRS screen.
Okay, got you.
Okay, thanks Lou.
So one of the other observers, Lu Shen, who was a graduate student at UC Davis, where Brian was a postdoc. I was a postdoc there a long time ago. She's now in China. So she's actually joining from China. She's going to hop in and join us. And what she's going to do is share her screen, which has some of the same displays that Brian has up right in front of him. So you'll get to see what the instrument and telescope controls look like. Okay, so now you see my colleague Lou has started sharing the screen that she has set up, which actually has multiple windows on it. So where Brian is sitting, you can see he has a whole host of monitors in front of him. Duplicates of 5 of those screens are up on the desktop that Lou is sharing. So you can see it takes a lot of various interfaces and control windows to run a telescope and the camera. So there are windows that show the status of the telescope and where it's pointing and what it's doing. If you see the bottom right window that says setup field in blue letters, in that window, you can see a bunch of text in the bottom right of that window. Those are the commands that tell the camera and the telescope what to do. So it'll say, move to a certain field, put in these filters, take an exposure for this long, and things like that. So Lou prepared that observing file in advance with our observing program, and the staff scientists at Subaru are executing it, and we talk with them as the night goes on, changing things as conditions warrant, or if there's a problem, pausing and things like that. In the top left of her window, you see something that looks like a target, a round circle. That's actually basically a view of the whole sky looking up from Mauna Kea. And it shows where the targets that we're interested in looking at, that's the sort of blurry white and green text. And then there's a little picture of the telescope and a little red line that shows where it's moving from on its way to pointing at the targets that we're interested in.
Hey Andrew.
Yeah.
Did you guys get a seeing estimate for the first half of the night, or any trends?
0.8 to about 1. What did you say? Oh. Oh. 1.7. 0.2, 0.7.
0.7 in H band or in a different band?
Which filter was that? Yeah, H.
H
Yeah,
band?
H band.
And that was a recent measurement?
Sorry.
That was a recent measurement or that was earlier in the night?
2 hours ago.
Yeah, sorry, I'm just trying to get a gauge because we're trying to balance breadth and depth of our observations. And so we've had pretty good luck with the last couple nights. And so we might push it a little bit harder if the conditions are very good and warrant it. So yeah, I'm just trying to get an idea of how long ago that was and maybe what air mass you guys were at when you were taking those observations.
I don't have a very recent one for us. CFHT has been reporting around 0.5 to 0.8 lately. And that is at air mass 1.02, yeah, around there, near Zeta.
Okay.
Yeah, there's
That's the gem.
yeah, it's
Yeah.
the dim.
Yeah, okay.
I found their mass is always very, very low.
Yeah,
I mean,
yeah. Well, that's without the ground layer, I think.
yeah.
So that helps.
But yeah,
If you ignore that, that helps. Okay, that sounds pretty good. So, okay, great. Thank you.
yeah, I'll leave that up.
And how often do we get a seeing estimate? Do we get it on the raw frames, or do you guys take it, or how do we monitor this?
Yeah. Sorry. Yeah, we check using can you see this monitor?
Yes.
So it takes and the auto level using the bright star in this page and for example this one level 6 star size is 0.4968.
Okay.
It doesn't can't see. But one is
The plate scale for this for swims?
HC1 thing. 0.5.
So the star size is in arc seconds?
Yeah, seconds.
Okay. That is very good. And that's one raw frame?
Yeah.
Okay.
So I continue check the same thing using this.
Okay. Perfect. Thank you.
Hey, Brian,
Yeah.
you can tell them that the field is good, is right. I just checked it with our finder chart.
Okay. So we have Lou on the other Zoom, and she just checked against our finder chart, and everything looks good in the field. So it looks like the pointing is good and everything, just as a confirmation.
Thank you.
So Lou, we're at 0.5 arc second seeing, in case you didn't hear, and no attenuation. So we're like 0.04 mags attenuation according to CloudCam.
Okay.
So that's pretty good.
I will write the log.
Okay, sounds good.
哎，
Brian, maybe you can tell them that anytime they're ready, they can go the science target.
So is this not a science frame that we're taking already?
No, we just took oh, they're doing focusing. Okay, let them do it.
Okay. So Lou, that artifact in the image here,
Mm-hmm.
what is
It will
that
be,
from?
I think it's from CCD or I don't know. And I think what they said is because of the edge of the filter, but what I think is due to the CCD. But it will eventually remove after the data reduced.
So this is a pretty big artifact. Is our dither pattern is big enough to?
No, it's the flat will take over that. Take care of that.
But but we are not getting photons there, as far as I can see. Is that correct?
But when I see the reduced image, it is not there. And even each frame, it is not there.
Is this window?
Yes. You speaking to me?
I see this window.
Yes.
The finding star for the lattice it's 0T1, but is it correct?
Sorry, can you repeat?
Yeah.
Were you asking?
Here they say something like finder chart.
Okay. So at the summit, they're asking us to confirm the field. Is
Yeah,
that?
it's right.
It's right. It's still the same field, right?
Yes.
Yeah. Okay. Yeah, we confirmed it. It's correct.
Okay, thank you.
Thank you.
Do you
Not really.
recognize that from the stars in the field?
So I'm comparing the finder chart I took from the Sloan data.
Got you.
So
Gotcha.
it's showing the stars.
I can
and
I
here-
can see those 3 stars. Yeah, I can see those
Yeah.
3.
So this 1, 2, and 3 is the same as what I see from like at Sloan image at the same pointing. So
In the right half, you see 3 more stars, and I can see those 3 stars in that image with the artifact.
yeah. So here is one. And
Mhm.
yeah,
I
this is
can't quite
one.
see your cursor actually.
Oh, okay.
Oh, now I can. Now I can. Yeah, when you're moving.
Okay.
Yeah,
so
I
there-
see those
there's
3
a
stars
small one.
exactly.
There's
It's a really nice asterism there.
Yeah,
The
yeah.
6 stars there. It's quite obvious. So Lou, so I still don't get it. So there's this dead spot in the CCD, you think? And so, okay, flat field's out, but still we're going to have an issue with not getting full depth.
Yeah, the one I stacked the image, the mosaic will cover that part. So it's not the flag, but the mosaic. But what I see from the image is okay, and we have a like quite a large radius on the dither.
Do you know the size of the feature and the size of our dither pattern?
I didn't measure that. I can do that really quick.
Which artifact are you talking about, by the way?
It's no longer visible, but there was in one of the
Yeah, I remember that. I remember seeing it in one of the earlier frames.
yeah. So there's a large. It almost looks like somebody put their finger down on the detector, but
Yeah,
oops, and then removed their finger really quickly, and so you only got a little part of it. But it looks like it takes up about a third of the detector in the Y direction, which is very large. You can kind of see it in the Jingo window there, on the left-hand column,
yeah.
second row down.
Mhm.
So Brian, I don't know if you as a host can do it, or if you want to add me as a co-host, and then we can annotate onto the screen. If that's useful.
True. That would be helpful.
Yeah, there it is. You just saw it.
Yeah.
So Ray, you're now co-host.
Okay, let me see if I can annotate.
I see it in some frames, not in others.
That is because there's a blue side and a red side, and
Gotcha.
then each side has 2 channels.
I see.
So it's only in one of those.
One of the 4. I see.
So for those joining us, this instrument is kind of neat. Usually when you have a camera, you can put in one filter and you take a picture through that filter. This instrument splits the light, and somewhat bluer light goes down one side and somewhat redder light goes down the other. And so you can put different filters on each side. And that's what we're doing. It's all infrared light. We're actually looking at wavelengths that are longer than we see with our eyes. So even though we see the pictures on the screen, the light that's coming from these objects is in the infrared. Because these objects are very far away, what we're looking at is light that was visible light when it left those objects, but has been stretched by the expansion of the universe to be in the infrared.
I take a first loop. Okay.
Okay,
Okay.
you said first loop, correct?
First loop.
Okay, great. Thank you.
So they've gotten set up, and you heard Brian say first loop. What they're going to do is take a picture, move the telescope a little bit, take a picture, the telescope a little bit, take the picture, and it's going to do that automatically. And that way we cover a little bit larger area, but also any defects in the CCD won't end up in the same part of the picture every time. So we can kind of average them out. And it takes us, one of these loops that we're doing takes 26 minutes. So while it's running, everyone will have a little bit of time to chat with you, and they'll just keep an eye on making sure that the images as they come out look okay and everything's operating all right.
Andrew, the size of our dither pattern, do you happen to know that?
The size is 20 arc second, Brian.
20 arc second is radius.
20 arc second radius.
Yeah.
Okay, thank you.
With a 9-point difference.
Brian, the structure is something like, the artifact is something like 35 arc second by 35 arc second.
So it's the detector, each detector is about 3 by 3 arc minutes, is that right?
3.3, yeah.
3.3.
3.3, okay. Interesting.
3.3.
And I kind of reduced, tried this chip on this chip, and it's removed. So I kind of feel like it's okay.
Okay, I mean, the size of the structure is quite a bit bigger than our dither pattern. It will likely have some differential effect on our depth, almost certainly.
On this part, yeah.
Right, but it's not like, yeah, but this part is fixed in detector space, but not fixed on the sky because of the dither pattern. So we're going to induce a kind of strange differential loss of light across the mosaic, which we should be cognizant of when we try to analyze the images.
Yeah, so that's why I was trying to make sure that the PA is right and it won't head on the overdense part.
Oh, okay, that's smart, Lou. Okay, so you've situated the pointing and the PA such that this artifact, is the artifacts only in the narrowband image?
Yes, only the only the blue part.
The blue side, which is the more scientifically interesting side for us, unfortunately.
Yeah. I think
okay.
I do the right that is not on our overdense part because the chip and the number of the chip and I think it's one on the right side and two on the left side. So it's kind of inverse.
Okay. But so the artifact is not centered at the center of the overdensity.
Yeah, I hope it's not. Like I was trying to set it now.
But we also have a 4 arc minute uncertainty in the in the end of the overdensity center. So maybe that's that our ignorance in this case is somewhat of a virtue.
Yeah, if this is really an issue, like maybe for the tomorrow, we can just flip all the target to 100 degree.
180 degrees.
180, yeah.
Yeah, I think that would be a smart idea no matter what, because this is going to affect the observations. And if we can spread that out as much as possible, as long as, I mean, the idea here is, especially for this structure, we don't really know where the overdensity is. And so we want to take an agnostic view. And so we want to have, as uniform depth as possible, so that if we're missing something, we know it's not because of the observations, but it's rather because there's nothing there.
Yeah. I think we can go that way. Like today we may have six for one pointing, and the other day we can have 3 on the inverse, flipped.
Okay, and we're trying to do a 9 loop depth still.
Yes.
Okay.
If possible.
And so
The other way is we can just split to 4 and 5.
But that would require doing something different this evening, correct?
Yeah.
Yeah. Okay, but so are we for sure going to go for full depth? Have you been able to make any progress on the reduction? I'm
doing it right now.
Okay. All right, so maybe we can decide as the night goes along what we think is prudent in terms of depth versus breadth. And I think trying to make it as uniform as possible, if we are going to go for 9 loop depth in each pointing, then trying to make it as uniform as possible would be good, which would mean 4 and 5.
Yes. Yeah, 4 and 5.
Okay.
We can decide one like at the 4th loop.
Yeah.
Yeah.
Sounds good. So we have about an hour and a half before we would need to decide that.
Yeah.
About 24
so
minutes.
For each loop, it will take 27 minutes, about half an hour. Yeah, just,
Okay. That sounds good.
And we're observing in the infrared, and so everything, the telescope, you, the sky glows and gives off infrared light. So if you just stared at the sky with infrared eyes or with an infrared camera and you added up the light, eventually you would basically overexpose the whole detector. So in the infrared, often our exposures are very short, and you have to take lots and lots of them. And then you add together all those pictures in the computer later on to make a deep picture. So when we observe a field like this with visible light, we might be able to expose for 15 minutes or half an hour, even in imaging. But in infrared, we're going 2.5 minutes in one filter and just over a minute in the other. And these are narrow band filters, so they don't cover a lot of portion of the spectrum. If these were broadband filters, the exposures might be 3 seconds over and over and over again. So Brian, do you mind if I take over screen sharing? I'll show some of the figures we used in the proposal, sort of explain what we're doing.
Not at all. That would be Lou, but I think you're a co-host now, so you can take
Yeah.
over. But maybe before we do that, we could just kind of introduce ourselves now that
Oh, yeah.
we're
Okay.
now that we're in a little bit of a relaxed state for the time being. So Roy, I think you already did some introductions at the beginning, but I can introduce myself, and then maybe everybody from the science team could introduce themselves. So I'm Brian. Hi. I'm actually a staff scientist at Gemini Observatory, which is basically across the street from Subaru base facility. I'm not on the summit of Mauna Kea, as Roy mentioned earlier. So I'm down at Hilo on the Big Island, which is, I'm about 500 feet above sea level. And so the people behind me that are on the summit, they're 13,000 feet above me, just to the west. So I can actually see them from the back porch here, if it weren't dark out right now. So I'm one of the scientists, one of the astronomers for this evening. I will pass to Lou, since Lou is running these observations and has been our superstar for the Subaru observations, to introduce herself.
Hi, hello everyone. My name is Lucian. I'm right now working at University of Science and Technology of China. I worked with Brian in my PhD and also Roy. So what should I say?
Do you want to say, Lou, like kind of like what we're observing tonight? Roy mentioned a little bit earlier, but we have kind of a special, I don't know, risky observation tonight. Do you want to explain a little bit what that is?
So tonight we're observing a potential like overdensity that found using the Lama alpha tomography. So in the Lama alpha tomography, you're seeing the light from the background source, and it will if there's a structure in the front, it will showing in the Lama alpha forest range depth, a lower like flux. So there's a absorption there. Using that method, so it's called Lama alpha tomography. Andrew Newman from Carnegie Observatory, they found this is called lattice, the survey. They found a overdensity at redshift 2.44. But when they trying to see how many galaxies there, they see not overdense there. So right now we're observing this target. So this structure, focusing on this structure and trying to see if there's galaxy overdense there. And we're targeting the, we're using a narrowband filter, narrowband 1326 to see if there's a O2 emitter galaxy. And we also have H3 band to hopefully see the H delta and O3 emission. That's what we are observing right now. Brian, do you want to add on that?
Yeah, I'll just add a few things. So just to maybe make it a little bit more accessible, we are looking at what we suspect is an overdensity of mass in the universe. So we suspect, based on this method that Lou just mentioned, which I see Roy explained a little bit in the chat. So there's cool gas, which is conglomerated, has accreted into this region of the sky. This is about 10.5 billion light years away. And so there seems to be a lot of mass there because there's this cool material that's fallen into this region. But for some reason, some weird reason, there doesn't seem to be any galaxies that have formed there. So we don't know why that might be. And it may be that we've just missed them in the past. And so we're going to try to look really deeply tonight. We're going to take pictures really deeply tonight to target galaxies which should be forming stars at a very high rate. So this is the singly ionized oxygen emission. And if we see some galaxies there, then that kind of makes sense to us. And this will be an overdensity of galaxies. And this is the kind of structure that we study, and hooray. So we get to do some galaxy evolution stuff. And if we don't see any galaxies there, then that's really, really a mystery. And we have to try to figure out what that means with models. So Preeti, would you like to introduce yourself?
Sure. Hi, my name is Preeti Steb. I work with Brian, Roy, Lou, Ekta, and also Professor Laura Lubin from UC Davis. I'm a third year PhD student. As I mentioned in the chat before this, I did electrical engineering and some theoretical physics. So you can definitely transition for your grad studies, no matter what your discipline is before that. And I study galaxies and clusters that are forming. Clusters of galaxies that are in the formation. And currently I'm looking at if they're forming stars or not. And yeah, that's my current project.
And I see Ekta just joined us. Welcome, Ekta. And maybe also, so Preeti, you're in Davis right now, Davis, California, right? And Ekta is not. Where are you joining from, Ekta?
I'm joining it from India. So it's around 4 o'clock here. And
in the afternoon, yeah?
Yes.
Yeah, you're luckier than us.
Yeah.
Here it's 1:22 in the morning.
Yeah. Hello, everyone. I'm Ekta Shah. I am a postdoctoral research scholar in this group, and I study how galaxies form and evolve in the early clusters that Preeti just mentioned. So clusters, when they are just forming, how does that kind of dense environment affect the star formation rate and other properties of galaxies? And for that, we use these kind of multivalent observations, both spectroscopic and photometric observations, which gives you a lot of information about the galaxies and their dense environment.
Thank you, Ekta. And Raja, would you mind introducing yourself for people who don't know you?
Absolutely. I'm Raja Guhatakutta. I'm a professor in the Astronomy and Astrophysics department at UC Santa Cruz. And I know several of you on this call. Casey Peters is one of the undergraduates at UC Santa Cruz who's been working in our research group. Brian used to be an undergraduate at UC Santa Cruz many years ago. We worked together then. That's how we know each other. I've known Roy for a long time. I met Preeti and Ekta yesterday. I know Arya because Arya's been connecting to our Shadow the Scientist sessions on many occasions. And I've been talking to Mariam Hamidi, who's connected from Iran and who's interested in starting graduate school in astrophysics in the US this fall. I know Pran, who's the organizer of Astronomy Outreach of Kosovo. She's a graduate student in the Earth and Planetary Sciences just across the plaza from me at UC Santa Cruz. I haven't been doing research with the group here on protoclusters, but what I have been doing is using telescope time that my research group gets to host the Shadow the Scientist sessions. And Brian, Roy, and I talked about trying this out with time that their group has received on the telescope, and that's really why I'm here tonight.
And so if you guys have any questions, feel free to put them in the chat. We're going to kind of just do a normal night on the telescope, we hope, without any excitement. There usually is excitement, but we want the good kind of excitement where we see something interesting rather than the telescope breaking or something like that. But yeah, so feel free to put questions in the chat or raise your hand, and we will try to get to your questions as soon as possible.
Oh, there's an excellent question about comparing to X-ray data. So often people do study galaxy clusters in X-rays. The reason we study them in X-rays, for those who don't know, is that galaxy clusters with their huge mass can hold on to very hot gas that's millions of degrees Kelvin, and gas that's that temperature emits in X-rays, just like the sun's corona. But these early clusters, these protoclusters of the kind that we're looking at, generally have not formed and had enough time to sort of make a deep enough gravitational well to hold on to gas that's that hot. If you know, the sun is in equilibrium between the pressure due to the temperature and the motion of the gas and gravity pulling in. In these galaxy clusters, it's the same thing. The gravity of all the mass in the galaxy cluster can hold on to this hot gas. In these early protoclusters, as we call them, they haven't sort of developed that deep gravitational well that can hold on to that kind of gas. So we don't observe these in X-rays. Even if they had that at this great distance, they would be very challenging to observe in X-rays. I don't know, Brian, you want to add something? Or...
Yeah, it's a great question, really great question. And it's a question that we're trying to address with these observations exactly. So these overdensities of mass can be traced by different things. So it could be this cool gas, it could be hot gas, as Roy just mentioned. There can be galaxies there. There may not be galaxies there for some reason, as may be the case in this particular structure that we're looking at now. But right at this distance away, so about 10.5 billion light years, this is kind of the transition period for these overdensities to move from kind of containing cool gas and very strongly star-forming galaxies to beginning to heat up that gas gravitationally and starting to quench the star formation in the galaxies that are in these systems. And so the system that we were looking at last night, which is called Hyperion, which is a known really big structure of galaxies at the same distance away. This system actually has small conglomerations, so they're not small, they're much bigger than the Milky Way, but small on the size of the scale of this object. So some conglomerations of galaxies which contain cool gas, so they're very young, where young means, you know, they formed 1 billion years ago or so, and other conglomerations of galaxies where we see X-ray emission. So the gas has already had time to heat up. And so we see a large diversity of these types of structures at this distance, and we want to understand what makes certain structures hot and contain galaxies which are not forming stars very much, and other structures where we see this cool gas and we see galaxies which are forming stars at a very high rate. And so that's exactly what we're trying to understand with these observations here. So we don't know the answer yet.
We have a question that says, what's the greatest discovery in astronomy? I bet you could have heated arguments over this. And we're talking today about these objects that are 10 billion light years away, and we know that, but 100 years ago, we did not know that objects could be that far away, and we didn't even know if the little fuzzy things that people saw in pictures were galaxies outside the Milky Way, or were the Milky Way was the whole universe. So one answer to that question would be learning that the universe is much, much bigger than we thought. Today, I might say that finding all these planets around other stars and understanding how common planets are might be one of the top 5 or top 10 discoveries. The expansion of the universe. There's understanding how the sun works, that it's nuclear fusion. I'm sure other people have other options that they can put in for great discoveries in astronomy. I think a cool one that we don't think about, or at least I haven't heard people say, is understanding that the material that everyone on this Zoom call is made out of was inside a star at some point. All of that carbon, all of that oxygen was made in a star, or a bunch of stars blown out into space and then formed into the Earth, and here we are today. I think that's a pretty top discovery.
I think it's also great that, because of the fact that we are, and all the stuff around us was made in stars, that also means that, the spectroscopic lines that you see in lab, in some ways that those will be the, like in hydrogen atom, those will be the lines that will be emitted in some distant star. So you can, in some ways, you can understand the spectroscopic nature of different elements on Earth, and then you can use that information to understand, these astronomical systems that are far, far away. So I think that is also super cool.
So Andrew, we're just going to do another loop after this. Is that right?
Okay, good.
We'll do loop 2 after this.
Loop 2.
Is anyone here a planet formation expert? Someone asked about rogue planets. I think there's actually multiple ways you get planets without stars. So there's actually no clean dividing line between stars and planets. So when we talk about rogue planets, those are typically super Jupiters. So they're things that are a few times the mass of Jupiter. And you can form those from the same clouds of material that form stars, and they're just failed stars. They just didn't have quite enough material to turn on nuclear fusion in their cores. And so that rogue planet, you could also think about it as a failed star. In some cases, you could have planets like Jupiter that formed around the star out of the disk of material that was around that star, and then there was an interaction with another star, and it got kicked out gravitationally, and that's why it's floating through space. And in some ways, it might be impossible to tell the difference, or maybe there are ways to tell the difference, I'm not sure. And that kind of distinction, planet, star, I mean, a star, you can think of it has or can have nuclear fusion in its core. And if it doesn't have that, then it's not a star. So sometimes we can make clean classifications, but just like we argue about is Pluto a planet or not, astronomers always start by classifying things and putting them into some kind of bins: elliptical galaxy, spiral galaxy, a rocky planet, gas giant. But inevitably, it's a continuum of objects, and where you draw the line is often not based in physics, at least certainly not at the start. So the answer to Arya's question is yes. Are brown dwarfs stars or planets? Generally, we think of a planet as orbiting another star. But what if you have a super Jupiter orbiting a totally normal star? Is it a failed star orbiting a working star? Is it just a big planet? So there's no clean answer. If it's floating through space by itself, is it a rogue planet? Or rogue planet sounds like a Star Wars movie. Well, Raja will appreciate this for us old timers, right? Brian's not quite old timer enough, but I was in graduate school when the first exoplanet was discovered. So I think the fact that the work that astronomers and other scientists are doing in other fields are basically rewriting our understanding of the universe in real time is really interesting. So 30 years ago, we didn't know if the fraction of stars with planets was close to 0% or close to 100%. We had identically zero understanding of what that number would be or should be. But today, our textbooks are writing and talking about exoplanets like we knew about them all along. But we didn't when I was in graduate school. So it's pretty remarkable how the pace of discovery is going on. And those of you who are younger and listening into this will be part of rewriting textbooks 20 years from now. I think that's really important to stress. In science classes in high school, often it's like, here's a bunch of facts and that's it. But it's actually, the cool part of science is that those facts are just a small part of the picture.
Exposure.
Yeah, so Mehul and I have been chatting about the fact that the first planets to be discovered outside the solar system were actually discovered around pulsars, dead stars. So you knew those planets could not sustain life as we know it. But technically, that was the first discovery of exoplanets. But those didn't get as much attention as when people started finding planets around sun-like stars. Good reason. No, that's not. All right, if you're ready for a little bit of trivia, one of our very basic units of time is an hour. It's 1/24th of a day. We measure how long it takes for the Earth to spin once, how long it takes for the sun to be at its highest point, 2 successive times, and take that time, we divide it into by 24. We call that an hour. Why 24? Because 24 has nice factors, divisible by 2, 3, 4, 6, 8, lots of factors. When we take an hour and we divide it into 60 parts, right? We call it a minute. Again, 60 has lots of factors, 2, 3, 5, lots of factors, 12, 15. The reason it's called a minute because it's a minute part of an hour. Minute. And the reason we call a second is it's because it's the second time you devise the unit. That's why you have hours, minutes, seconds, and you also have degrees, arc minutes, and arc seconds. Apparently in Newton's Principia, there's references to the third minutum, the third minute, not the second minute, but the third minute, which is 1/60th of a second. So this is a little bit of trivia. Astronomical trivia.
You guys, I am only connected on this Zoom. Can one of you share your screen? I can't see what's going on.
Roy, do you want to show something, or I can share the screen? You're
You
muted.
can share the control screen back.
Okay.
So Lou, just so you know, we just got another seeing estimate from the summit, and it's holding steady at 0.5.
Okay, thank you. Great.
So this is really good. And we're still waiting to transit, so we're still at 1.1 air masses, so hopefully it should even get better.
It's actually a remarkable observing run for the winter.
Absolutely incredible, yeah.
And the Mauna Kea has weather. It's very cold and snowy in the winter. So getting a row of clear nights with good atmospheric conditions is not that common. And we've had a lot of nights this winter, including Christmas. The telescopes do not close for Christmas, most of them. Actually, some of us here were observing on Christmas Eve. We did not see Santa.
I was worried about JWST running into Santa.
It was, I think we were on the telescope when it got launched. I wasn't personally, I was sleeping.
I was up.
I was.
I was waiting for my stocking to be filled. You were up.
Acta and I think.
Yeah.
Should have taken some narrowband images of the.
That was Mossfire, I think. So that was on Keck. So that was very precious time. And no narrowband imaging. I was actually more excited to see that that our observations went through that night, because that was sandwiched in between two very crazy storms on Mauna Kea, and we just barely got the dome open on Christmas Eve, and we observed Christmas Eve and then Christmas Day night, and then another storm rolled in about 10 hours later and closed us for about a week and a half. So only 2 nights in December, I think, that were observable, or the last half of December that were observable on Keck we got. Lou, if you stop sharing for a second, I can show pictures from the summit right now.
Sure, yours.
So this is what it looks like this is what we're looking at, kind of. So this is from the Gemini Observatory. Let me move my Zoom screen. So these are pictures from the Gemini Observatory pointing in different directions on the summit of Mauna Kea. So this is a atmospheric cloud cam. So this is a satellite. This is looking straight up from the Gemini Observatory. And Gemini Observatory is located just about half a kilometer to the south, let's see, southeast of Subaru. So if you look at this picture here, the north cam, this is two telescopes which are just adjacent to Subaru. Subaru is just off to the left in this picture. And then this is looking towards Hilo, where I am. And different parts of Mauna Kea. And you can see planes moving around in the background, but we're basically at the top of the world here. And you see all the clouds passing by. And luckily those are not high enough for it to affect the observation. So we have a nice clear sky for tonight. And this is very rare for this time of year. So we're very excited to be able to observe. You can see snow on the ground from those previous storms, but nothing tonight.
Mauna Kea is at some seriously high altitude. I remember when I first started observing there, I sort of used to hesitate to call it ground-based observing. It didn't sort of seem like it. It felt very lunar to be on that mountaintop.
It's truly an amazing place.
Yeah, because back then there was no remote observing. You had to go to the summit. I started observing in 1995, and it was just a brutal experience. Jet lag, sleep deprivation, and oxygen deprivation combined.
That sounds pretty normal for you, Raja.
That's true.
Even,
Two of those things.
even when we went down to Waimea, there was at least two of those things.
Two of those things. 2 out of 3 ain't bad. Is that the
Roger,
moon in the lower right picture?
What's that?
Is that the moon in the lower right picture?
The moon is passing by. Yeah, and that's probably glare on the camera from the moon. So I think the moon is about 70% to full tonight. So yeah, it's very bright. It'll probably be setting in, my guess is about hour 15 minutes. Yeah, Subaru is one of the only telescopes that you can still go up to the summit to observe. So in fact, had we really wanted to deprive me of oxygen tonight, we could have requested that. But since my house is about half a kilometer away from the base facility, I decided I would be comfortable not going to the summit.
We haven't been on-site observing since the pandemic, actually.
Really?
Yeah.
So you guys don't allow anybody up there since the pandemic?
Yeah, at least. Since the pandemic.
Yeah, I got 3 nights up there in 2017 using Supreme Cam, which was absolutely amazing. And I spent most of the time with the night vision goggles.
Fair enough.
And we had one. What's that?
Oh, I definitely spent quite a bit of time with those night vision goggles.
Yeah, as if the mono weren't absolutely amazing enough at night, that seriously enhances the experience. We had one of our collaborators that was supposed to be driving the telescope start to get affected about halfway through the night by oxygen deprivation. And so we stuck him in the massage chair as he was laughing maniacally. And he passed the rest of the night in the massage chair as we drove the telescope.
Yeah, we do have to keep an eye on that. It's not at all uncommon for people to have poor reactions.
I heard you guys got rid of that chair up there. Is that right?
It died, but we got to replace it.
Oh, okay.
We still have one.
Okay, I will request summit observations the next time if the pandemic abates. Just another reason to root for the pandemic to abate.
Exactly.
But yeah, in theory, Subaru is one of the only telescopes that you can observe from the summit as a guest observer. Raja, did you ever do Keck observing from the summit?
Yep.
So already
Roger,
in
you, yeah.
2002, I guess 2003, when I first started observing with you, it was required to be in Waimea.
Oh, I see. Okay.
Roger, you and I observed this. That was my first year on Mauna Kea too. Was 1995.
Okay. Yeah, I remember observing with Elris then on the summit, and then with NERC. I remember what other instruments. I think by the time Demos came online in 2002, we were working from Waimea.
Yeah, my first run was definitely in Waimea.
Was that, what year was that, right? 2002?
That was late 2003, early 2004.
Okay. So I'm wondering, I think perhaps when Demos was commissioned, well, certainly the commission, people who commissioned it went up to the summit, but I think maybe the first observing might have been at the summit too. I don't remember now. It's been, and with that lack of oxygen on the summit, I've forgotten everything. But I do remember being on the Keck 2 telescope on its second and third night of operation. And that was back then, for some reason, the semester that time started in October, not August. There was some shift of the semester, maybe because of the commissioning. No, actually it wasn't the semester. The Keck telescope went online on October 1st of 1996. We were on second and third, and the segments kept failing in the sense that there would be this automatic voice that would come on, and you would see the guide star break up into 36 parts.
Is this the ACS is not settled?
ACS is not settled. It was Sharon Schutz's voice, who used to work at Keck. It was her recorded voice that we started to, it was like you started to dread this in the middle of the night, hearing that voice.
Yeah, now you only hear it during Amira.
Now you only hear it during Amira.
And yeah, so the Keck 2 telescope that Raj is talking about, that's the telescope on the left on the top right picture here. So kind of
north view.
In the north view, yeah. So
that's what you guys were using last night, right?
That's what we were using last night, yeah. And then the telescope just to the right of that, to the east of that, is IRTF. So it's a NASA-run facility.
I think it was during my first observing run, which was at the summit. I think with NERC at that time, we did NERC at the summit, followed by Elris in Waimea, I think. But at some point during the middle of the night, all the alarms in the telescope start to go crazy. And like, what's going on? And the telescope operator's keyboard on an old Solaris workstation, the letter Q got stuck in the down position. And it just sent like 10 million Qs to the telescope control system, and all the software just crashed.
I think history has a sense of humor, because even tonight, I saw the first half observers, some keyboard got stuck on period. And for about a half an hour, there was just period showing up on the screen. But I guess, let's see, 25 years of technology has allowed us to not crash the telescope when you get a keyboard stuck. So it seemed like things were going just fine, even though somebody had stuck the keyboard down.
You're probably too young for this, Brian, but Solaris workstations did not take to things being unplugged. So replacing the keyboard was not like you could do it on your computer today. It actually would take down the entire workstation. So it took down the entire telescope control computer to replace the keyboard.
Raja, I think the computer that I used in your office, in between bouts of sleeping on your office floor when I was doing Z-specking, was the Solaris machine. Am I remembering that right?
I think so. I think that's right.
yeah, that was definitely a trial by fire as an undergrad using that machine. So I can stop sharing now if you want to reshare your screen so that people can see our exposures.
Now I feel like I'm talking like an old man, which is evidenced by my gray beard as well. But when I was an undergraduate student, I worked with Hubble data, some of the early Hubble data, and it was sent on those big giant tape reels that you see in movies. So you think of Hubble as being this advanced technology, but the internet wasn't fast enough to send the data to the university. So they just FedExed boxes of those big reel-to-reel tapes. So there was a time in my life I knew how to load those into tape readers.
Right, did we were at Tololo at the same time also, right? We were saying last night.
Yeah, so I went to Tololo twice in
Okay.
the summer of my junior year at college, so something like 1992.
Okay.
And then the year after 93. It was either 92 and 93 or 93 and 94 in the US summer, Tololo winter.
Well, the winters there were lovely. It was so beautiful. I started going there, I think, in 1988, and I did part of my thesis on the 4-meter at Tololo. Wow, that looks so biological, this image. Like a dead bug.
It's not a compliment, is it, Raja?
Thank you. I'm always full of compliments like that. But you know, I think I must have gone to Chile 25 times. And one of the things I remember about Tololo is just how dark the skies were. Really, there was no light pollution at all. There were these strange creatures called viscachas that would come out at sunset and watch looked like they were sitting there watching the sunset, except they were looking for the insects to come out so they could eat them. But they were somewhere between a squirrel and a rabbit.
So Lou, you say when you reduce a single frame, when you flat field, what do you see on the flat field of this of the narrowband images? I mean, do you see the feature, and what's the level of flux that you see relative to the adjacent pixels?
I think
It's a
so.
really imposing feature. Like Raja's not kidding about it. Like somebody just squished a bug on top of
It's a bug, it's not a feature. There you go.
Ah, I see you're back to this stage of the night, huh, Raja?
That's right. It's getting late enough in the night.
Just wait until somebody asks about dark energy versus dark matter, huh?
You're going down a dark road, Brian.
Right.
Oof.
Yeah,
Oh,
this is
boy.
the flat.
So that's the flat field.
That's an asteroid, I'm sure. Looks so much like a rock.
Yeah, it looks like a topo map or something.
Pran,
Oh,
that's an asteroid.
It looks like a dune worm.
Yeah, kind of looks like it.
Pran has an asteroid named after her. And she's discovered a different asteroid, but this one looks like an asteroid.
G,
I have an asteroid.
What's that?
yeah. Okay, what's-
Another loop.
Good seeing.
No, get another loop. It's done.
So you're moving on to loop 3 now, is that right?
Yes.
I think. Now I'm being the loop C. Okay,
Sorry, I don't quite understand. So you're done with loop 2 now or no?
now loop 2 finished.
And so we can start loop 3?
Yeah. Start C. Loop C.
Yeah, that sounds good.
Yeah.
And sorry, were you mentioning something about the seeing or did I misunderstand?
Okay. Point 5.
4.5?
Not change.
No change. That is great. No change is great. We'll keep that.
Yeah, that defect on the chip sure looks like a deposition failure or something failed to adhere in one of the layers or something like that. So it does not look like we should have sensitivity there, but I don't know, or coding failure.
But you see the counts depreciate by quite a bit, right, in the flat field. Like, so yeah, I mean it's a really imposing feature. I think we should really try our best to mitigate it. So they said that it's the edge of the narrowband, but I mean we're using a different narrowband this time than we were using last night, and you saw the feature last night as well, right?
Yeah, it's not definitely not the filter. Because I like on their website, it's there. Maybe I didn't took that very close look. Let me show that. I'm showing it on the share screen. So this is the website of Swim, and here's the right. So you see that structure is already there.
That's a broadband filter there, right? That's just the J
Yeah,
band.
this is J band.
Okay, so I would say we flip. I would say we
Okay.
flip after, I guess after loop 4, yeah.
Yep.
And so we'd have to update the OP file for that. Is that right?
Yeah.
Inside the summit?
Yeah, they can modify it there.
Okay.
But just in the beginning, the target, we define the target in the beginning. So we can create another one, like add a flip.
Yep. So I'll just
name on the
call
flip, and then the PA,
underscore flip. Yeah.
yeah, and the PA is 180 degree.
Yeah.
Thank
Okay,
you.
great. I will. I'll let them know. Thanks, Lou.
What is this thing we're hearing from time to time that sounds like a child's voice? Is that some kind of echo?
So that is telling us, that's an alarm from the telescope, letting us know that the exposure has started. And
Got it.
so we're getting a reverberation because we have the sound from the summit and also the sound down here at the base facility. So it's saying start exposure.
Got it.
But yeah, it's a child's voice, I think. Or somebody with a lot of helium in their system. So yeah, Raja, you'll see every time you hear that alarm, the dither number, so the one in blue screen that's just to the right of the colon, that number will go up by 1. So we've moved the telescope and then we're re-exposing.
Which number goes up by 1? Sorry, I don't think I'm seeing the.
So it's the one, I think the one that just got covered up.
Okay.
But yeah, so every time that number.
Oh yeah, 3 of 9. I see that.
Exactly, yeah. So the number will change, and this countdown
I see
will stop and then go back to 75 seconds. So we take a 75-second exposure, move the telescope, and then begin the exposure again.
Got it.
So I'm going to step out for about 10 minutes to run over to Gemini. I'll be back. Lou or Roy, if anything goes wonky up on the summit, can you guys jump over to the summit Zoom?
Okay, and after you come back, I'm going to bed.
Okay.
Okay.
All right, thanks.
I know people have been talking about dithering, and if you're, dithering is generally a negative word where you can't make up your mind about something. And in astronomy, when you're doing imaging, dithering means you can't make up your mind about where you want to point the telescope. So you point it here, then you point it there, then you point it somewhere else. And exactly as I think Roy was describing, that it's because all pixels on the silicon detector don't have the same sensitivity. And while you try to correct for that, another way, we try to correct for that through a process called flat fielding. But another useful thing to do is to take this, this way your star of interest lands on different detector pixels each time. So you sort of average that way as well. I just looked up the dictionary definition of dithering. We astronomers have co-opted these terms. Every language, I guess every science, every subject co-opts terms. And dithering. Mehul, are you using archival CFHT data or new data?
Are you talking to me?
No,
Sorry.
Mehul was put a note in the chat saying near Earth objects. He's using CFHT to study near Earth asteroids, and I was wondering whether that was archival data or new data.
You mean the broadband we're using?
No, sorry, Lou. I was there was a mention in the
there's
chat.
a question.
Yeah, in the chat. Sorry.
Sorry, I didn't.
No, sorry,
get
I
time to
wasn't
check
clear.
the chart.
I was mixing my media. There was a question in the chat. I was trying to give an audio answer, or I was asking an audio question. Got it.
We were talking about this artifact on the CCD, and it might be strange for people to see that our images have all these defects in them when you buy an iPhone or Android phone and the images look pristine. And that's because the detectors that we use are not, even though they're similar types of digital detectors with the same underlying technology, they have much larger pixels. They're physically much larger and have much higher sensitivity. And so they're typically manufactured more or less one at a time, as opposed to millions of iPhone detectors. And they're just, when they make iPhone CCDs, they test them, and the ones that have defects, they throw them out. But these are so expensive to manufacture that we cannot afford to make 20 and throw out 10 of them. So we get what we get, and we don't get upset, as my little kids say. They don't practice it, but they say it.
From the mouths of babes.
So someone asked if we have backup sensors. Answer is generally no. So if you have a significant instrument failure, that could be days, weeks, or months, depending on the problem. All these telescopes have multiple instruments available. Usually you can only have one or two mounted on the telescope. Gemini, where Brian works, is interesting. It can have, I think, 3 or 4 mounted at the same time, and they can easily swap between them. Some telescopes like Keck or here at Subaru, you can have an instrument at prime focus and an instrument at a different focus, and you could maybe switch once a night between them. But yeah, these instruments are all unique and one-off. So I was making the comparison to iPhone detectors, but it's not just the detectors, the actual cameras are all very specialized and large and expensive. So the instrument like Demos that we were using on Keck another night, or on Christmas actually, that's like 10 feet long and 6 feet across. It's a big cylinder instrument that sits on the deck of the telescope dome.
フォーキャストでスコープ2使えた？まだ使ってない。え？
まだ使ってない。
あ、オッケーオッケー、いいです。多分動くと思うから。まあいいや。はい。ということで、それだけ。今、小山さんのモスファイア観測中。
We're talking about people having different expertises. So building these astronomical instruments and designing them is its own sort of specialty within astronomy. And an instrument like this, I don't know what this one costs, but the Keck instruments are typically 5 to up to almost, Roger will know better perhaps, but like $30 million for the more expensive ones. And that's because every component has to be custom made. You know, there's almost nothing you can, well, some cables and wires and things like that, but basically everything else is made at a machine shop at the university or a custom fabricator or things like that. I think it's funny that in movies, they still show astronomers looking through telescopes, their eyeballs, sometimes at least. In my professional career, going back to the early 90s, I've never done that except for giving a visit to the public on the 88-inch telescope on Mauna Kea. They would once a year put an eyepiece on that telescope and you could look through it. They don't do that anymore.
Did you say 80-inch? Right.
Okay.
Did you say 80-inch? Like 80?
Yeah, the 88-inch, the University of Hawaii 88-inch. So that's the first large telescope that was on Mauna Kea. It's still operating. It opened about 1970. And it's what, when data started coming from there, that's what really demonstrated Mauna Kea as a superior site. It's just being roboticized now. So they're putting robotic adaptive optics system on it. But our grad students use it a lot. It's done used for a lot of follow-up with Pan-STARRS discoveries, and I've observed with it many times. Not in a while, but oh, someone's asking, what is it to get into astronomy. So James, I see your question. We can get to that in a little bit. So to go to a career in astronomy, at least in the United States, and most parts of the world that I know, is you go to college, and then you have to go get a graduate degree, what we call a PhD, and then it's still challenging to get a long-term position. The things that you need to do are be good at math, be good at computers, and one of the things I think about is to be creative, so to have good ideas, and also, depending on the kind of astronomy you're doing, to be careful so that you good at paying attention. Roger, do you know the average seeing on Mauna Kea? Probably about half an arcsecond, maybe 0.6.
I would have guessed more in the optical. I would have guessed more like 0.8 in the optical, but I don't know. Well, I suppose it depends on the site, because CFHT that ridge gets better seeing than Keck. What's the question about Mauna Kea overall?
Median from, here's a, Subaru says 0.65.
Okay. Is that for a particular telescope or?
That came from Subaru.
Okay.
Google said when I put in Mauna Kea median seeing, and I got something from a webpage at Subaru.
Okay. I think it's slightly worse than that at Keck and better at CFHT possibly.
CFHT claims that the atmospheric seeing is 0.4 seconds.
Wow.
Which I can attest to because I have taken data in the optical at 0.4, even 0.38. I think is the best I've ever seen in Keck. Visible. Yeah, so James, last night we were doing spectroscopy. Tonight, this project is a little bit complicated, but last night we were looking at the same field as we were looking with Keck. Pictures by star-forming galaxies. That's what we're doing tonight, but for a slightly different project. So these emission lines, so bright emission in a narrow wavelength range, and we're trying to identify those. You don't get quite the same exact detail about them as you get with spectroscopy, but you can map a bigger area and see where there are star-forming galaxies. So it's just a different approach to a similar problem. Okay, so James, Lou, are you okay to check them for the next loop?
Yeah, I can do that. I will stop the sharing, if that's okay too.
Yeah. So actually what I will do is, I'll wait for you to stop and then, all right, now I'll share mine. Let me see if I can find it. So, this part of the figure here, you can see there's wavelengths in nanometers across the bottom and flux, or the transmission. So this blue curve shows one of the filters we were using last night on Subaru. And the red curve is the other filter we were using. So this camera actually takes pictures, has two separate sides that can take pictures in two different filters at the same time. And this bluer filter, which is at 1.3 microns or 1300 nanometers, corresponds to singly ionized oxygen at the redshift of the structure we were looking at last night, Keck. And this other filter just so happens to correspond to doubly ionized oxygen. And both of those features, emission features, are produced in star-forming galaxies. So if the object looks bright in these narrowband filters, but in broadband filters that cover a much broader wavelength range, they don't show up, then they're probably star-forming galaxies at this redshift. So we're using this same trick with these narrowband filters to try to see if there are galaxies in another part of this nearby part of the sky where people have identified absorption from hydrogen gas, but have not seen lots of galaxies. So we're trying to see if there's a mysterious big agglomeration of gas.
Once this done, we can do another one.
Galaxies before. Oh, Agapios, I'm sure there's Mauna Kea has been studied extremely extensively and expensively for its conditions. So probably you can just get that answer from Google for those metrics. So Gemini says that the sky at Mauna Kea is fainter than 20.8 magnitudes per square arc second for half the time.
Can we do another loop?
Yeah.
Thank you. And is that so we're gonna have another pointing. So it's the same pointing, but like 180 degree. I didn't have that in the OPU file. So can you help us to create one there?
And so Lou, the plan is to do one loop at this 180-degree flip at this pointing, right?
Yeah, I think if everything goes well, we can do 6.
We can do 6 total, so 2 of this new flipped pointing.
2, yeah.
Okay, so we'll do 4 of the original position angle and then 2 of the 180-degree flip, and then we'll do the same thing for the second pointing.
Yes. Yes.
Or we may as well go 3 and 3 tonight, and then just in case something happens a different night and we're not able to complete it, so that at least we get half and half for the second pointing.
For the second pointing, half and half.
Yeah, we can
Yeah.
go 3 and 3 if we have enough time to do 6. Then we can go 3 and 3.
Yeah. I think we probably can cover like 6 for pointing 1 and 5 for pointing 2. Yeah, 5 for pointing 2.
What
If everything goes well.
what time do you have us going up until for the science observations without the standard?
6:20.
You have us observing?
Yeah, that's it. Yeah.
Whoa. Okay, so 12-degree, if I remember well from last night, is like 6:08 or something like that.
Yeah.
So we go way past 12-degree with our science observations.
Yeah.
Whoa. Okay. That's surprising.
Yeah, but actually at the final frames, I think the background is getting higher, so I'm not sure
Yeah.
whether it's worth taking.
Yeah, because normally when we're observing with Mossfire, past 12-degree, you're doing a little bit better in the morning than you are at the evening, but past 12-degree, it's really bright.
I think so. Yeah.
Yeah, the problem of the standard star is it takes a long time for the telescope to screw to it.
Mhm.
Like 10 minutes.
It's a big telescope.
Yeah. So like last night, I decided to take the standard star.
Oh, okay.
Because one is the scene is very similar to the night before. And like everything goes well. And when I reduced the data, I didn't use the standard star for now, and for marks, no.
Okay, I honestly think so not for the reason that you said, but I honestly think we can get away with this because we are observing in the cosmos field, and so we have so much. So we know things, you know, are not like, for example, stars in the field are not going to be excess in the Paschen beta filter relative to, you know, H-band observations that already exist in cosmos. So we can do the same calibration that we did with Works before, foregoing a standard star. So I think that that's fine because in the end you just in the end you just do a standard on a grouping of objects and you forget about the standard star. So I'm totally comfortable not taking a standard star for that reason. I wouldn't say that the seeing being the same is necessarily a good reason to do that. I think we have photometric conditions and we've had it for the entire time, so we've been really lucky. So that's another good reason that we might get away with one standard. But ultimately, even if we took a standard every night, we would post-process this with photometry in the cosmos field, just like we did before with Marks. So I think it's totally fine. But I would suggest we monitor the sky brightness over time. So starting maybe at around 6 o'clock, and we start to see where it gets pretty bright, and then we just stop there, because I think that's the background is going to get pretty ridiculous at some point.
Yeah, I didn't have time to check the data, but I can do that very quick.
Okay, we can also just check. I mean, it doesn't hurt anything taking those frames. I mean, we're not planning anything else with the telescope, but it probably is not helping. So we can check tonight and just get a basic gauge of how late we can go, and that can kind of set our plans for the next 2 nights as well, to know what we can fit in.
Yeah. Okay.
Okay. And
yeah, approximately 6:10 is fine.
Yeah, that sounds good. The other thing I was thinking of as I was walking back from Gemini is that I think it would be ludicrous at this point to try to go for breadth. So I think it's a bad idea to not go to full depth. And the reason for this is because if we not because we necessarily need the depth, I don't know that, but we need that feature taken out. And we will have no flip data at this point for 4 of the pointings. So assuming everything goes well tonight, 4 of our pointings, all 4 of our pointings in Hyperion will not have a flipped PA, which means that this large artifact will be affecting a considerable portion of the field, given that it's larger by quite a bit than our dither pattern.
Yeah.
So when we median combine the data, it's we're going to have some serious issues if we don't do a flip observation.
So do you think it could be better if we have a larger dither pattern?
I think flipping is going to serve the same purpose. So I think it's okay. Given that these are fairly small field of view for swims, I wouldn't want to go too much bigger, and we would have to go like a little bit larger than the feature size in the detector, which would mean dithering by almost an arc minute, and that's not a good idea.
That's really not a good idea.
Not a good idea. Yeah, so we would introduce some other differential depth effects just by virtue of doing that. So that's not a good idea. And I was speaking with Ichi, who I think probably came in here at some point, and he confirmed that is an actual defect on the detector. So it doesn't have anything to do with the band or anything like that. So I think that sets our observing plan, because, and you know, assuming everything goes well, I think that sets our observing plan.
Mhm.
I don't think we have a choice anymore.
Yeah.
But we made the right decision for tonight. We made the right decision because we did end up going with the 2-pointing strategy with lattice rather than the 4-pointing strategy, which would have caused us to not be able to come back to the Hyperion observations.
Yeah. Good that you're here and decide that.
Cool. So that makes our job a lot easier because the swims detector decided for us. It wasn't me that made the decision. It was the swims detector that decided for us. So I take no credit for that. Yeah. Okay, sounds good. So so after this loop, we'll do the flip and then we'll try to go for, so you had 3 and 3 planned or 3 and 2 planned for the second pointing to move us to 620 or so?
Yeah. Yeah.
Okay. All right, so we'll go 3 and 2 then.
All right, Brian, Lou. I'm gonna go to bed.
Okay, I will go over to our link and share the screen.
Yeah.
Brian, could you tell the add the object?
Yeah, I'll talk to them. No worries. Yeah, I got it.
Okay, thanks everyone. Thanks to everyone who joined us. I have to wake up in 4 hours to get my kids to school, so
Thank you, Roy, for joining us.
yep, that was fun.
That was super fun to have you here.
At the Shadow Scientist stuff. So thank you all for joining us. We'll do more of these in the future, or other astronomers will do more of these in the future. We don't have any observing nights for a little while after this week, right? So,
but I think Raj is going to start up again in February, so there won't be too much of a lag. And then Marusha's group is going to do it. So yeah, we'll definitely have some other events coming up soon. But for now, maybe get some sleep, Roy, since this is your second night in a row of getting 4 hours or less than sleep.
this is actually going to be night.
Roy, thank you for including me, and I'll reach out to you. Maybe we'll set up a Zoom call with Brian just to strategize about what went well, what we might do differently in the future.
Yeah, and I would like to advertise this to people at IFA know that this is happening. So
Excellent.
since we have all the telescopes, I think one thing we'll definitely have to think about is how to coordinate with the observatories to get them sort of
right. Yeah, there are several things I'm thinking about that we've done differently. For example, we assign specific blocks of time, not the whole night for STS. That's one of the things we might consider. Anyway, we can talk about it. And I should be able to provide some logistical support for this, meaning event planning support, some astronomy expertise support to, sort of to help ease the burden on the people running the experiment.
Yeah, and I can do that too from the Hawaii side.
Would be great. That would be terrific.
Okay.
Thank you again for including me. Really appreciate it.
Bye, everyone.
Good night, Roy.
Good night.
And I see Sarah has a hand raised. Is that an accident, or do you have a question, Sarah?
Sounds like it might be an accident. Brian, I have something for you.
What's that?
I'll put it in the chat.
You misspelled it, Raja.
No, I know. That's what it's meant to be, a pun.
Yes, I'm joking.
You
None of
think I
the other
should-
transitions give a good pun though.
Sorry?
None of the other transitions make a good pun. You're bracketing me in here. I don't know what else to.
No, that's true. Yeah, that's true.
Don't know how to make a comeback.
Yeah. NSF funding. Isn't there a Fund series after the Passion series?
After bracket, I think.
Yeah. Oh, yeah, that's right. It's the, let's see, it's Lyman, Barma, Passion, bracket and then fund. Yeah.
How fun.
Yeah.
Well, luckily we're not observing any of those tonight, so
True.
we don't have to anger you, Raja.
No, you don't.
Africa.
There was another good one in the chat there by Mihal. He or she's asking you to be truthful, Raja.
Don't lie, man. Yes, exactly. Very good. Very good.
Hey, Andrew, you guys hear me at the summit? Yeah.
Mehul, your pun was in the top bracket.
So we're gonna do I don't know if you caught what Lou mentioned earlier, but we were gonna do a flip on this pointing. And we were hoping that you guys could stick it in the OPE file. So after this loop, then we would flip 180 degrees and then do 2 loops at that orientation.
Okay. I'm not an expert on the swim syntax, so I'm going to grab the support astronomer.
Okay, thanks.
Do you have some change on E5?
Yeah, so for this pointing that we're on now, we were hoping to flip 180 degrees. And this would be for the next loop and the following loop. So for loops 4 and 5. So same RA Dex center, just 180 degrees flip. So PA of 180. And the same, we would like to do the same also with pointing 2.
PA change?
Just a PA change, yes.
Brian, one more for you in the chat.
Exposure. Exposure.
So were you guys able to get that flip in?
So, have you checked whether it's the field of view is correct?
You're talking to me?
No, talk with yeah, the Shohei, the sport astronomer.
Okay.
Yeah, sorry. Yeah. So Shohei, you flip the position angle by 180 degrees, right?
On the TV?
You were asked to rotate the position angle by 180 degrees, right?
So this is after this current loop. So hopefully we're still at the same position angle for this loop. And then
I think
have we been
we're
flipped?
gonna flip 180 degrees, right?
Yeah, after this loop, yes.
っていうんでいいんだよね、多分ね。
180 degree?
っていう話をしてなかったさっき。
Hey, Brian, can you tell them to make a new one?
I think with their change, not until
Make a new target.
the current file. So this is a backup, it's different position angle.
So this is yeah, if you guys can just modify Shui, if you can modify this to add another pointing, just to call it like backup underscore flip or
Yeah,
something.
or yeah, flip is better, I think.
Yeah, and so we want to keep this one still the same because we may come back to it. And so then just add this other one, which is at PA 180. And then we'll go to that after the next two exposures, after this loop is finished.
All right.
So basically just cut and paste and then flip 180, that's all. And the same thing for P2 underscore backup.
Yeah. これも一応ちょっと確認しますけど、これってバックアップっていうのは180度回すために新しくて。
違います。もともとバックアップという名前。
So I see there's a couple of questions in the chat about why we're doing the thing that we're doing right now, asking them to flip 180 degrees. So if everybody can see in the top left of Lou's screen here, there's this giant artifact. So this giant thing that looks like a squished bug or something. It's a Rorschach test basically. And that's actually physically on the detector. So there's an issue with the detector. And so somebody astutely mentioned that 180 degrees flip, it's going to look the same in the sky, but we're actually rotating the detector around 180 degrees. So that artifact is going to move on the other part of our observation. And so we're going to hopefully, we hope, we're going to average it out. So meaning that we're moving the telescope, this dithering pattern that Raja mentioned earlier, which is good for telescopes. We're moving the telescope around so that we can kind of average this out. But this feature is really big. And so our movements are fairly small compared to the size of this feature. And so by rotating around 180 degrees, we'll do, half of our observations where the feature is on the other side of the sky, our field of view. And so it won't be as bad in our image. This artifact won't show up as bad in our image because we're able to average it out and move it across our field of view. So we can move the detector. We can't move the sky, but we have the ability to move the detector. And so that's what we're going to do to try to mitigate this issue.
PA イコール PA が2個ダブルで入っちゃうと大丈夫。どうなのかな。なんかまずい気がするから、多分オブジェクト名の方をいじるべきだと思うけど、これもさっきどう指示されたかをまず
なんか、まあ、結局、僕もわかんなくなって急になって。
バックアップっていうのはどういうモチベーションで入れられたんだっけ？
そもそもバックアップという名前で、天体の提供されたっていう。
最初からね。
最初から。で、今日の観測天体はアンダーバーバックアップをやってくださいということで、
はいはい。じゃあ、これの180度回転したのが欲しいってね。
だから、そうそう、このはずだと。
変えないとまずくて、これをコピーして、で、バックアップのフリップ180っていうのをしてくれっていうことだと思う。
I deleted the P. The P in backup.
Oh.
And Shui, you may want to call this lattice 1BF for a short name, so we can differentiate it.
Yeah, I think so. Yeah, F でいいと思う。1BF.
Yeah, that's perfect for us.
You need underscore or what is that?
No, I think it's okay.
That's 1BF.
Yeah, it's okay.
Yeah. And so as soon as this exposure is done, we're happy to go there. And then we do the same with 2B when we have a chance.
Start exposure.
So Michal, you asked a question about the image being flipped on the vertical axis. That's exactly right. So we're going to mirror the image on the top left. And so the artifact which was affecting just below those, so it's actually to the south of those kind of 4 stars on the right hand side there. We're going to take the good detector, so the left detector, we're going to stick it over there. So there'll be no effect in that region of the sky, but that defect will move over to the other region of the sky. So there's actually no stars visible there in the image, but if there were stars exactly mirrored along the vertical axis there, those would go away in these images, but that's kind of the point, so that we average it out.
Oh, wait, never mind. It's maybe it's this. This. No. Oh, okay. No. May I see?
Move telescope.
I can't remember what that is.
Target change to the flipped version.
Move telescope. Alarm. Less than 1 minute to rotate on limit.
So you guys just moved back to the original pointing center and you did the flip of 180. The flip is going on right now.
Yes.
Great.
It's actually under options. Can embed the logs so they won't pop up. They'll show up in here, right? Yeah, we can go back to first.
So I see there was a question in the chat about how much time it takes for a project to finish. I'm curious if if maybe Lou or Ekta could speak on this, since they have recently finished projects. Ekta recently finished her PhD, and Lou finished her PhD about 2 years ago. But what's the development of the timescale of a project, and what are the kind of bumps along the road, and what do you do? So maybe Ekta, could you speak to that at all?
Sure. I don't know exactly who asked question, but if you are a student, I just want to make a clear distinction. So in the usual studies, when you are, for most of the courses or most of the degree courses, the course is usually limited to the books, right? And the syllabus is limited to whatever is in your book. The difference between that and PhD is for most part of your PhD, you're doing research, and that's new stuff. And so in many ways, in some ways you have the, it's your responsibility, and it's up to you to define like how large of a project you want to take. So let's say, if I have some data, so for my PhD, I studied the effects of galaxy interactions and mergers on their star formation rate and black hole activity. So I already had some data, and then me and my advisor had kind of planned out like what we want to do at what stage, and we had rough plan about what each of those steps will be how much time will be taken for each of those steps. And the thing is, like, if you're doing PhD properly, you will be trying something new. So there will be bumps on the road, and you will try out some methods, and some of that will work and some of that will not work. So we have a saying like things are always going to take longer than you estimate. So for my first project,
we could probably let's check real quick. Maybe a short exposure to check.
Yeah. Okay.
And Lou, I guess you have a finding chart for this. We can just flip it in our heads, but I think we've seen this asterism enough that we can probably that we can probably pick it up pretty quick.
Yeah.
Let's say we have a rotated. Brian, it seems more, is this okay?
That seems right. Yep. I see the 2 stars. Yeah, no, that looks perfect. Yeah, let's go ahead with that. Lou, you concur?
Yeah.
Yeah, that looks good. So we're ready to go. Thanks, guys.
okay, I'll continue.
Yeah, please feel free, Ekta.
Yeah. So for my first project, I was basically extending some of the methods that were done in the local universe, and I was extending those methods to study high redshift universe, so very early universe. And that came with its own challenges. So it took me about 3.5 years to actually develop the method properly. And after that, I finished my second project, which was using similar data, but instead of studying the black hole activity of galaxies, I studied the star formation rate in galaxies. So that only took me like 1 additional year. And then in that year, I also studied the same things like effects of galaxy interactions and mergers on their star formation and black hole activity. But instead of using observations, I used cosmological simulations. And because I had already developed methods using observations,
You're okay, Ekta.
Okay,
Fine.
so because I had already developed my method using observations, I was able to complete the second observation project as well as same projects using simulations. So overall total 3 projects in just 1 year while completing my PhD. So so it really depends on your project and how much you want to, include in your dissertation or include in your final project. And I kind of joke with my friends like, usually somebody would be like, oh, like somebody couldn't finish a project, a PhD in like 5 years, like why is it taking so long? But as I said initially, like it's up to you how much you want to include. And in many ways, when you're towards the end of your PhD, it's not like you are towards the end of the project. It's more like you have more and more opportunities to expand it. So imagine like, you are in some dark corridor and then suddenly you take a turn and then there are your favorite stuff, like, like I like flowers. So imagine more and more flowers there. And then you are only given like, 5 minutes to grab as many flowers as you can. But then the more forward you go, the better flowers you find. So you're like, I also want this and I also want that. It's similar for PhD as well, because like when you're towards the end of your PhD, you have already done so much, and it's just, if you just do a little bit more, you will be able to expand it even further. So at that point, it's like, include as much as you can. So that's why it becomes difficult to like wrap it much sooner. But that's what makes it awesome. Like you can do so many new stuff, and that's what makes it worth it, and worth your time and worth your efforts. So yeah, I hope that kind of answers your question.
And really the job's never done, right, Ekta? Because as you say, you see more and more beautiful and complex flowers as you go along. Your vision also improves. So you have better instruments that you use, but also your mind is able to interpret the structure of those flowers in a way that you weren't able to 2 or 3 years ago when you started. And so you just finished your PhD not too long ago, but finishing is just a start, because now you're joining our research group and you're expanding out into still grounded in what you were doing before, but expanding out into even more complex science and from many different perspectives now that you potentially weren't doing before. So the answer is probably that it's never finished. And you spend an entire career doing it, and then somebody else takes over afterwards, and maybe you've answered a few questions if you're lucky, but then there's even better questions that your research has allowed for.
Sure.
Yeah, I agree with Ekta that it really depends on what your expectation and ambitious, and I found that in the beginning of the PhD, the graduate study, it took a very long time to even read a paper. I think like Pretty also like said that.
That's because you were reading my papers, right?
Not only yours, but like Laurie's. Like our groups, the paper is very long, and sometimes like the words, it's just okay, I don't understand, and just not following the sentence. It's very easy to get lost in the beginning, but when like you read more and more, and like I do a more like myself, like experience more in the data and analysis, I found it's much easier to read. And this I found reading paper is easier when I finish one paper. So at that point, I feel like, okay, I can read one paper really quick, like go through it, like just understanding it, get the main idea. That's easier when you finish one paper. And yeah, I've done 3 projects in my PhD, but it's a series. So the first paper is using already reduced radio data. I'm doing radio. My focusing is environmental effect on galaxy evolution, and I'm using radio data as a tracer to the whole galaxy group, but their radio emitter. So the first project is using archival data, and then the second one is also using archival data. But in the meantime, I'm reducing new data, our own data taken from VLA. That's a very large array, something like that. Yeah, very large array. It's amazing radio telescope. So while I'm doing the first two projects, I'm also reducing the third one, the more data, and that came to my third project. So the first one took a long time, and then the second one and third one is much quicker. Like I forgot the initial question. Actor, do you remember what's the question for us?
It was something like, how long does a project take?
Oh yeah, okay. The first one took me like 1 year, 1.5. The second one took like 1.5. The third one just took like half year, and the third one took half year, and the fourth also like half year. Yeah, so it's getting quicker.
Also, go ahead.
Yeah. You go ahead.
Are you guys
I was-
restarting the detector controller or something now?
Yeah, yeah,
Okay.
yeah. It's now responding the, if they place it for a while, probably.
Okay,
It takes several minutes.
okay. So Lou, we were having an issue here. If you see the most recent frames, the detector is not reading out very well. So when we rotated, something happened with the detector readouts. So they're now restarting the detector controller.
Okay.
これダメだな。一遍オフにしてもらえます。
There was some issue with the detector yesterday as well, right? Like with readout.
今 B
Yeah, in the beginning, I think.
オフになってます。
I see Roy's note that in the beginning, like there's readout problem.
Yeah, so I think that the last set of frames was no good.
じゃあ、テクスチャオフにします。テクスチャオンにします。トラップアウトプット000に。はい、じゃあこれでちょっとパワーアップしてください。
Can you go to monitor? Yeah. Can you see real quick? Just want to take a look at that. Yeah, it's exactly.
Okay, じゃあ、ブルーの方ですね。
Yeah. No, it's okay.
10秒の時は起こらなかったんですこれで。
はい。
終わったらセットアップフィールドでもう一回戻して、それで10秒取ってもらって。Okay, we're back online.
Move telescope. Order.
Okay. Perfect.
That looks very good.
Yeah, okay.
And hold up the loop.
Order.
Hi, Brian.
Yes.
Do you mind ask them like to scroll up the frames to let me see which frame is bad, so I can write it down. What's
To
the
scroll-
frame I
To scroll down on the frame screen or what?
scroll up the frames, so so I can see like I can see which frame is bad. Like when I reduce the data, I will take a look them, like remove them.
Sure, but which like how are you able to tell? Because I see, so you're talking about the frame screen on the fourth VNC window, that the prefix is SWSB.
Yeah, yeah. Or you can ask them, they may know.
Okay. Guys, do you happen to know which frames were the bad ones? Where the detector didn't read out well?
Frame number.
Yeah, the number.
Nine to 891, from 9 to 891.
92891.
971 blue arm, and 102781 to 102951 red arm.
Did you get all of that, Lou?
Yeah, I can see that in one of the VNC.
Yep.
So I could see a fixed pattern in the CCD a little while ago. Is that some kind of doping pattern? Look like rings.
Yeah, I see it too, Raja. Yeah, I'm not sure.
I can sort of see it here, yeah.
The ring.
Right, Brian.
Pattern caused by OHL growth.
Yeah, these sort of look like rings at the lower left, you see?
Yeah, I think this is something due to the filter.
I think
This is
it's due to the doping pattern on the detector, I think.
We were just told that it was from OH air glow lines.
Oh, okay, fringing.
This is a pattern caused by the filter, medium band filter in HVAC.
I see. So the it's fringing in the filter, is it?
The fringe caused by the filter.
I see.
Yeah, that's correct, Roger.
I'm having a little bit. Brian, I have a one-liner for you. It's not good, but it's a one-liner.
Okay.
I just put it in the chat.
So you're gonna be here all night, Raja?
Sorry?
You're gonna be here all night, is that right?
I don't think so. I don't know how much longer because I have a 10 a.m. meeting in the morning.
Do you want to
It's
just
not-
start your stand-up routine now, or
I'm already doing my sit-down routine. That's right.
Okay.
You know, I have been sitting in this spot in the couch for the last 2 years, and my family, the shape in the couch is lovingly referred to by my family as the Great Depression. There you go. There's my sit-down routine.
Yep, perfect.
I'll reach out to you, Brian, about the planning going forward. While this is still fresh, it'd be good to chart.
Okay, that sounds good.
We still have a whole, I mean, we have a big group, 55 people right now.
So we had a couple of questions in the chat while we were doing some telescope stuff. So I see somebody asked, why don't galaxies have a natural magnetic field like the Earth does? So actually they do have, so the interstellar medium, so the space in between stars, there is a presence of magnetic field there. And actually, before I started working with Raja at UC Santa Cruz, I worked with a professor there named Stephen Thorsett, looking at pulsar, so dead star signals from dead stars. And we were looking at what's called rotation measures, which were induced by magnetic fields in between the pulsar and when we receive the light on Earth. So there's a lot of physics actually that people simulate in simulations of galaxies that try to reproduce these magnetic fields and then see what the consequences of these magnetic fields are for the emission in galaxies. And so this is a really open, I think it's one of the most under-constrained problems in modern astrophysics is what these magnetic fields look like in galaxies and how they affect the evolution of the galaxies.
Exposure.
Can I add one quick thing about the discussion on the project's lens and stuff?
Yeah, please.
So I just wanted to say that, the projects me and Lou discussed, they were for our PhD dissertation. So, you can also have projects that are well suited for like high school students or college students or, uh, like almost anybody with some educational background and some training. So when you define project, it's like, what question are you asking? So sometimes we already have a question like, we want to study how galaxies grow over time. And sometimes you already have data and you want to know how much more you can study using that data, right? So when you imagine if you already have data, then you can start with something simple, right? Oh, how does this quantity vary with this quantity, or how does this quantity grow over time or something? So, so you can ask some simple questions that can be, studied, that can be, I guess, resolved based on some very basic experience with programming, or even basic experience, even basic math sometimes. So, so that's why like the length of the project will depend on your question and will depend on how you want to design it. So yeah, don't feel that, all the projects are like take years or something. You can have a smaller project, and you can also have projects that are like, career long, that are like mysteries. So yeah, so there is quite a range.
Exposure.
So I see there was also a question about the hardest thing about while doing a project. I'm sure like the most famous or the most interesting astronomical discovery, we could all have different answers to this question and argue over it. I noticed that Preeti mentioned coding as being a really hard part of doing a project. That's certainly true for me as well. So writing code and doing it in a way that gets to what you want in a reasonable amount of time, and just trying to conceptualize what kind of tools you need for the project is probably one of the hardest parts. So not only coding, but which telescopes you need, which kind of observations do you need, but also what are the questions that you're trying to answer. And as you start to take these observations, so you may think, okay, one tool or one code that I've written is really, really good for a certain type of question. So I have a question like, what's the magnetic field in this galaxy, or how many stars are being formed in this galaxy? And so you start to write something and you think, oh, I'm really smart for having written this thing. And I got time on this really big telescope and I'm taking these observations, which should really help me. But the universe always surprises you. There's always different ways of looking at the problem, or you find yourself interested in something else. So it comes to light as you're observing or as you're running your code that maybe that's not the right question to ask. And so then you have to adapt to that, and you have to get different observations, and then you need to use, because time on the telescope is very precious, so you need to use all of those observations together to answer both your original question and new questions. So keeping grounded in what you're doing, where you're headed, and what's interesting to you, and what are the questions that you're trying to ask is important, but then also being open and being adaptable, so that you're not imposing on the universe your understanding and your questions are the right ones, but rather that you listen to the universe, what it's telling you, and you then start to, you know, create tools and do different observations to lead in the path that it's kind of leading you. So I think that balance is one of the hardest things in any scientific discipline, because that's not just unique to astronomy, of course. But there's plenty of other hard things. So giving talks, I think, so trying to tell people what it is that you found is very complicated. So I mean, of course, these observations, we start with the idea to take some observations on the Subaru telescope. Then we have to convince people that those observations are actually worthwhile. And then we plan for many days to take these observations. And then we sit here at 3:27 in the morning taking these observations. And then we have to analyze them, see what they mean in terms of the questions that we asked. And then we have to present them to people so that everybody knows what we found. And so that process takes a lot of different skills, and it can be very hard at first. But over time, you can develop the skills to be able to do each one of those stages effectively, and then to present your knowledge, what knowledge you've gained to the world, so that other people can use it and then ask even better questions themselves.
I just wanted to chime in on something Preeti said at the end there. I 100% resonate with that. Science is a team sport. It's not an individual effort. And I hope people who are eavesdropping on this experiment can see that it's totally a team sport. There's a team that's helping run the telescope at Subaru. You know, there's a team of scientists on the Zoom call. There are other people who are not on this call right now who will contribute. It's very much a team sport.
Yeah, so if you look at any scientific paper in the astronomy community, it's very rare that you see just a single author writing a paper. A lot of times it's going to be at a minimum 5-6 people that are all working together, that are taking different observations, that have different expertise, and that work together to try to make a coherent picture of the observations or the theory that they're working on. And so I think the communication between what seems to be like disparate fields of science or astrophysics can also be a very challenging part of the process. So if you're really used to studying like stars, and then you're working with somebody who's used to studying galaxies, trying to make a communication between the two sets of knowledge can be very challenging, but very worthwhile. And that's in fact where a lot of really good discoveries come from, is people coming from very disparate areas and getting together, working together as a team, and by virtue of the different perspectives, being able to answer questions that they would never be able to answer alone. I see we're getting a lot of questions here. Probably more than we can keep up with. Okay, so there was a question about galaxies looking stationary and why do we say that they rotate? So this is a project that we can't do that this evening because we're not using a technique called spectroscopy, which is what we used last night on the Keck telescope for our Shadow the Scientist event. But when you look with spectroscopy, you break up light into its constituent parts. So you have you're able to see an entire spectrum of light. So thinking about like a prism, you see all the way from blue to red from a galaxy, and you can actually, if you place an observation in such a way that you look at one part of the galaxy versus another part of the galaxy, and it's oriented in such a way that so if you think of a spiral galaxy, if it's facing right towards you so that you can see the whole galaxy, so probably pictures you've seen of like the Milky Way, or they're supposed to be of the Milky Way, it'll look like a big grand design spiral that's face on looking right at you. That's of course not the Milky Way because we don't have cameras out there, but that's the idea. So that's a face-on spiral, and then you have an edge-on spiral, so where it looks real thin like a pancake. And so if you have something like that and you're able to orient your observations such that you're able to see both sides of that galaxy, you can actually measure the Doppler shift, so the shift in light from one side of the galaxy to the other side of the galaxy, and you can measure the rotational speed of that galaxy. And so a lot of galaxies are measured to have rotational speeds 100, 200 kilometers per second. So very, very fast rotation on our human scale, of course. On galactic scales, that's very, very slow. And so when you take a picture, even 200 kilometers per second, you take a picture, let's say 2 hours apart, that's 7,200 seconds. You'd think, oh, that's a really big movement. But galaxies are very large, and so you don't actually see them change on a human time scale. So you can only measure that with the spectrograph.
And Brian, you may have said this already, but the sun takes 200 million years to go around the Milky Way once. 200 million years, and that's a pretty typical number for the rotation period of a galaxy. That's why you don't see them in a human lifetime. You don't see them change. Sorry to interrupt, but does that make sense?
Yeah, no, thanks, Raja, for clarifying that. Yeah, so it's a really long time. So pictures are you're just getting a snapshot. And so when we're looking at things in astronomy, we want to take snapshots of different things at different times, at different distances, because things aren't going to change on it. Well, there's a few things in astronomy that do. We talked about one of them last night called a tidal disruption event. But on human timescales, not a lot happens out in the universe. So we need to take pictures of different distances, which are traveling back in time, and then try to make a picture of how, let's say, a model of how those pictures connect to one another. So it's kind of like archaeology.
And one other thing I was going to say, Brian, is a good way to think of why it takes the sun to go, a good way to order of magnitude calculation. The sun is located 25,000 light years from the center of the Milky Way. So light traveling in a straight line would take 25,000 years. If it were just traveling from the sun, if the sun were traveling straight towards the center of the galaxy at the speed of light, it would take 25,000 years to get there. Now, of course, the sun isn't traveling in a straight line to the center of the galaxy, it's going in a circle. So instead of r, you have to multiply by 2 pi, which is about 6. So instead of 25, it now takes 150 or 200,000 light years. Now that's traveling at the speed of light, 200,000 years traveling at the speed of light. The sun's speed is 1,000th the speed of light, 1,000 times smaller than the speed of light. So instead of taking 200,000, it takes 200 million years to go around. Sorry if that was quick, but that's a order of magnitude way to calculate how long it takes a galaxy to spin.
Thanks, Raja. Okay, so yeah, quite a few questions here. The closest star, so Raja just mentioned the closest star, that's the sun. So that's about 8 light minutes away. The next closest star is Alpha Centauri, and I think that's about 4 light years away, something like that. So it takes about 4 years for the light for Alpha Centauri to arrive here at Earth. So if Alpha Centauri blew up today, we wouldn't know that until 2026. So that's pretty far away. So we're kind of a little bit alone here in this solar system. So it's a good reason to make the best of it. And then there was another question about Pluto being a planet. According to the official astronomy dogma, Pluto is not a planet. It's something called a dwarf planet. It used to be a planet, designated as a planet, but about, I would say 10 years ago or so, at the International Astronomical Union Conference, they decided that there's this new class of objects in the solar system called a dwarf planet, of which Pluto is, I believe, the largest. And so right now it's currently classified as a dwarf planet, not a planet. So there was a good question here for Lou and Ekta from Marcin about, in the end, is it worth the struggle that you have for your project, or is it, I mean, would you be here tonight if it was not worth the struggle?
I mean, it's absolutely worth it. Oh, obviously, I'm here and I have been here, I have been observing for like past week or more. Even though I'm like visiting my family after 4 years, and each second is totally worth it. So I think, but I know people who joined PhD and later on they found out that it's not for you, it's not for them. So I think what I would suggest is, a lot of times, especially in astronomy, people would like look at pretty images of galaxies and, they will find it fascinating and they would be like, I want to do this. And when you actually do astronomy, like for your research, you realize that for most times you're not actually staring at just pretty pictures of galaxies, right? For most part, you are kind of doing coding, as Brian and Lou mentioned. So I think it's important to realize, like, whatever field you want to kind of join for your career, it's important to realize, like, what do people who actually have that profession do for their day-to-day stuff, do for that day-to-day work. And for that, at least for research, you can, try to see if you have like opportunities to join like undergraduate research during your undergrad or something. And then that will at least give you some idea about whether or not research is for you, or whether or not, let's say, astro is for you. So I would strongly suggest to get things like that. Yeah.
Or Ekta, I need to talk to Brian for a second.
Yeah, sorry.
We're gonna do another
So Brian,
loop.
I always want to ask you that if we do another loop on this pointing,
Yes.
then we may not like have 5 total for the other pointing.
Okay, and this is our fifth loop, correct? So we had 4 at the
Yes.
other position angle, and then this will be the 5th. Okay, yeah, I think that's prudent. So why don't we move over to the other? So we'll take 3 loops at P2 backup, and then 2 if everything goes well, 2 at the flipped position angle.
Yeah, I agree. Yeah.
Okay, sounds good. I'll let them know.
Thank you. Ekta, you can go. Sorry.
Yeah, no, I will go.
So we're gonna forego this last loop. So we're not gonna do the 6th loop here. And we'd like to move to our second pointing. So P2 underscore backup.
Okay. So the next is last loop.
Yeah, so as soon as this loop is over, then we'd like to move to that one. And actually, since we're already rotated at 180, we may as well go to the flipped one. So that way we don't have to rotate back to 0. And then we're gonna eventually go to the original pointing. So maybe we could do P2 underscore backup underscore flip first.
Okay, P2. Okay, I make a P2 flip. Okay. So that's the final loop. Okay.
あれいいのやっちゃってよかった。
あれファイナル、次がね、ネクストがファイナルってますでしたよね。なんか聞き間違えた。
自信なかったら聞き返した方がいいよ。
Sorry.
Not done.
So
Not have another object.
Finish? Sorry.
Yeah, we just wanted to move to the next one so that we did 5 loops here.
Oh. Okay. Already. Yeah. Okay. I'm finished the 5 loops. So
Yeah, so we can abort this and we'll go to the P2 underscore backup underscore flip. Yeah, you need to make it.
Yeah, that is to be. Yeah, I'm making. で、
Yep, looks great.
で、
またロスが走ってるので、こっちをまずキャンセルしない。待ってね。ちょっと待って、止まったんじゃない？慌てない、慌てない。まず状況を把握しよう。まだ走ってるよね。
キープエクスポージャーが、
セットアップフィールド。
field lattice 2DF.
Yeah, that looks good. And Lou, you have the Finder chart ready?
Yeah. It should be flipped, so it's not the flip one.
Right. So we'll be observing the flip one first, so that we don't have to rotate.
どんどんやっちゃいましょう。
今まだ終わってない。
今、ピンポンって言ったよね。
さっき終わってない。
終わってない。
ちょっと変な気がするので、キャンセルで切りします。
ちょっと待って、じゃあ、その止める前にログを見て、ログとかはそっちを見て。サクセスフリーフィニッシュになってるよ。あれ違うかい、ハルトがあって、ステータス。
青リンゴになってるんですか？
青リンゴになってるよね。
青リンゴもなってる。
完了した青リンゴじゃない。
なんかプログが動いてるとか、ローテーターが回ってるとか。
全部止まってると思う。
で完了すると、ここの緑シェードが消えるので、終わってないんですけど。
ログのタブで、
ステータスかな。タスクマネージャーゼロなんだけど、そこには何も出てない、確かに。キャンセルですよ。それしかないね。
レコードした結果とかずらーっと出てるワードがありませんか？
ストリート、モニターかヒストリー。
なんだろうな。ログじゃなかったかな。ログの中の、
ESC、VGW ステータス、ESC を見ないといけないんだけど、今できてないんで。
Hey Brian, is there an arrow showing up?
Wait a minute.
Or is before?
一旦これはキルするしかないかな。
What's that, Luke?
Is there an arrow, like the sound? Because of arrow?
Yeah, I think we're just trying to get the movement into the queue so that it's they're picking it from the OP file.
Yeah.
And they're having a little bit of issue, but I think it was just more of a had to do things write it in the right way and then enter it into the queue the right way. So I think we're there. We'll probably start exposing. Yeah, that's a better sound. Yeah, so we're doing the short exposure now, and this is to verify the field.
あ、全然違う。
Okay, so we just have quick field.
Yeah, it's good.
Lou says yes.
Great. Okay.
僕さ、で、
Yeah, so we'll do 2 loops here is the plan, and then we'll flip around 180.
Yes. Thank you, Brian.
Ah, okay, I finally see finally found the field. Okay, yeah, looks good. You picked it up very quickly.
Yeah. It's very clear.
We have a nice foreground elliptical galaxy just off the field of view.
Yeah. Acta, I think you can continue. We're on like target now.
Yeah, I think I was done. Do you want to answer that question?
Oh, I just forgot the question again. Okay.
It was something like we talked about our projects. So I think the question was like, was it worth your time and efforts and energy,
Person energy?
Like time and efforts and energy, like you spent so much time working on this project, so much of efforts and energy on working on this project. Was it all worth it?
Oh, okay. I think this should go to Brian, this question. Does that worth it?
I think it should come to me.
Yeah.
That's the most linear. Yeah, yeah, maybe Raja. Is it worth it?
No, let me, I think short answer is yes, but what makes it worth it is what I want to say. I think the most important thing in my journey, I've been a researcher for 36 years. My most important part of my journey is the people I've come to work with, the people I've looked up to, the people who've looked up to me. And it's been an amazing group of people. I mean, and this is again coming back to the fact that science ultimately is a human endeavor, it's a team endeavor. A distant second is the fun of tackling big, fun, complex projects, or inspiring projects that are big in terms of time, mass, distance. That's a distant second compared to the fun of working with some of the most amazing people. I would say it's totally worth it. Yes, the Earth did rotate faster in the past, to answer the question. But the slowdown rate is 2 milliseconds per century. That's how much longer the day is getting.
Start exposure. Move the telescope. Start exposure. Start exposure. Move the telescope. Start exposure. exposure.
Okay, somebody else should answer this question. Is it hard to become an astronomer?
Preeti, why does somebody else need to answer that question? Are you not an astronomer?
Not completely yet. I haven't finished my project.
I think you're observing on a very large telescope right now. That
Right.
constitutes astronomer.
Okay, I guess so. Thanks. I guess, well, in some sense it is, and in some sense it's not. It all depends on how excited you are about what you're doing and how enjoyable you find what you do day to day. So I love being able to observe like this. I love my group. I love my mentors. They're the most supportive people I've had in this field. So on all those academic fronts, I really enjoy it. The hard part for me is coding, struggling with that, and not being able to come up with smart questions. Now that's my personal journey. So I think the answer varies depending on where you are philosophically, mentally, I guess, and also the people around you, the community you have. At my old school, when COVID wasn't happening, I was able to work with people in the same a room, so we would help each other and things were easier. Now that everybody's isolated, it's a little harder. So I think it depends very much on the situation and also the people who are mentoring you and your friends that would help you with whatever struggles you're facing at the time.
So I can speak to that a little bit. So thank you, Preeti, for answering. And yes, you are an astronomer. So you're at a different stage in your career than Lou or myself or Raja. Yeah, so we're all working as a team of astronomers here with different levels of experience, different backgrounds. So my position is a staff astronomer, staff scientist at one of the telescopes on Mauna Kea. And so that's a permanent position. So I've already got my PhD and I've gone through getting a postdoc and then a second postdoc and then eventually a permanent position at one of the world's foremost telescopes. And so that is difficult. It's not, there's no reason to say it's not difficult, but I think most things that are worthwhile are very difficult. And it took a lot of years of study. So I had to put up with Raja for 3 years at UC Santa Cruz. So that was probably the most difficult part of my journey. But
what I had to put up with you? What?
But still, I persisted after that. No, Raja was great. And Raja set the bar very high for my future advisors and future mentors. And so actually having worked with Raja at the very beginning of my career really helped me understand, first of all, how to approach astronomy in a way that was humble, but with tenacity and with intense curiosity. And so armed with that, 7 years of graduate school, followed by essentially 10 years of bouncing around to different positions, different postdocs, temporary research positions, applying for grants, applying for telescope time. But it is absolutely worth it in the end. I never would have done it if I don't enjoy it. It's taken me to all over the world, living in the south of France and now living in Hawaii and in California and Santa Cruz. It's hard work, but it pays off when you see all these wonderful images that you're taking of your own volition, of your own ideas. And Preeti says that that it's difficult to ask smart questions. I think we all have difficulty with that. But as we work together as a team, and as we have supportive people around us and people from different perspectives, and we are allowed to use these wonderful telescopes, wonderful instruments to help inform us, our ignorance, to shine light on our ignorance. We work together and with these instruments to build up a picture that is incrementally different than the picture that we had previously. But that is how the knowledge works, the state of knowledge in science and the state of knowledge for humanity. And sometimes there's these giant leap forwards that we talked about previously. So like Edwin Hubble taking observations and understanding that, more than 100 years ago from a telescope in California, understanding that these little blobs of light were actually other galaxies in the universe, and that these galaxies were receding and that the universe was expanding. So those are big jumps forward. Here, when we're taking these observations, of course, we can always make a discovery that's absolutely amazing and mind-blowing. And that's a wonderful part, but also these incremental gains are really interesting too. So it's hard, but it's worth it. Absolutely. So there was a question from Lana about what the different screens represent, the ones on the screen share here, and the best programming language to learn for a career in astronomy. So you definitely don't want me to answer the second one, because I use a programming language that's antiquated. So I'll answer the first one, and maybe the younger crowd can speak to the second one, although I know what their answer is going to be. So what we're looking at here, and Luke can correct me if I'm wrong because I'm not an expert in these observations, but in the top left here, we're looking at an image. So this is an image, this is probably a narrowband image. So this is a very narrow, so it's a filter in front of the detector, which allows a very narrow amount of light in at a certain wavelength. And so we're seeing some stars there. This is just a really quick exposure. We're stacking or combining tens, if not hundreds of these kinds of exposures to go really, really deep. So these are just bright stars in the field that we're looking at, and we're looking for galaxies that are much, much fainter than these stars. In the bottom left, I'm guessing that's probably a weather. Yeah, so that's kind of monitoring the health of the instruments, the temperature of the different optical parts of the telescope. So there's detector temperatures, so internal to the instrument, some benches, all these different parts of the telescope. We want to keep an eye on how hot or cold they get, because this can affect what we see. So if things get too hot, the detector doesn't work very well, and so we're not able to see the kind of images that we'd like to see. So we want to make sure that things stay flat on that graph, so that we can keep seeing the stars and galaxies and not the inside of our dome or the inside of our instrument. On the top right is a kind of mosaic of images. So these are thumbnails, so different observations that we've taken. This is each individual detector, different observations. This is a live feed. So I think the one on the left, it was just our acquisition image. So that one's kind of static for now. It's just showing our initial very quick image. This is going to actually read out over time. So this is actually what we're seeing at the telescope now with the pictures that we're taking. And then at the bottom right, this is our control interface. So the people on the summit of Mauna Kea, the Subaru folks at the summit of Mauna Kea, they're using this to control the detector and the telescope. So all these everything that's written here in the bottom right, these are different commands to move the telescope and to change the settings on the detector so that we get the kind of images that we want to get in the places of the sky that we want to get them. So this could change around the filter that we're looking through. This can move the telescope, rotate the instrument. This can change the exposure time. And so you hear this, what sounds like a child's voice in the background. All these lines here, all this stuff that's written, this is actually what is making this voice sounds. This voice is telling us that we've moved the telescope and that we're starting a new exposure. And you can see an exposure is reading out just now. So this is the previous exposure that we've taken, the previous picture that we've taken, and then we're moving the telescope and taking a picture again. And so for programming, I use a language called interactive data language, which is a proprietary language. So meaning it's not free to use, but a lot of universities have licenses so that you can program with this language. You can write your own programs, and it won't cost you anything. And so I use that in my current job at Gemini Observatory. But we also use a programming language called Python, which was popular with the youngins. This is a free open source software programming language. And in some people believe that it's more adaptable. There's a lot more user support, that you can do things with it that you can't do easily with other programming languages in astronomy. Or you have to at least write your own code to do the same things that are already there for Python. So sometimes that's good because you have to do your math yourself. So for example, when I was in graduate school, I spent about, I don't know, probably 3 weeks programming something in IDL to understand how much, if you're moving in spherical coordinates across the sky, how much you need to move in one direction versus another direction to get to the location that you want. And that math is quite complicated, and the programming is quite complicated. And eventually I got it, and then I realized at the end of it that there was already so I did all that programming in IDL, and then realized there was a Python package exactly for that, which I could have downloaded in 30 seconds and used. So, but I learned the math and I got it right. So. Yeah.
We largely use.
But math is more fun, right?
You guys use Python here mostly?
For most things, yes. Even all pieces that are written in Python.
Okay. So yeah, Subaru uses mostly Python. Gemini, we use about half IDL, half Python. But I would say the future is Python. So if you're getting into a native language, Python is definitely the way to go. Yeah, I noticed C++ was also mentioned. That's something I used in the past. It's not very pervasive in astronomy, but there's some really cool packages in C++. I'm not like a super awesome C++ programmer, but there's like really good visualization software in C++. So it's definitely worth learning if you're getting into astronomy, but it's not the main package, not programming language that's used. I don't know, Ekta, or Preeti, do you do any programming in C++?
Just a little bit. I did not like it.
Yeah, it's much less intuitive.
Yeah.
IDL and Python are very intuitive languages. They almost read, like once you start, it takes a while, but once you start to get into them, you can read them like a book. C++ is not, and like Perl is definitely not. I did some programming in Perl a long time ago. That was very painful.
Yeah, it definitely seemed more daunting to me when I was trying to learn C and C++, but Python seemed a lot easier to get a hang of.
Yeah, and IDL and Python have very similar syntax. So if you can read one, you can read the other pretty easily. Programming is a little bit tougher, but like all the Python programs with Gemini, I can read no problem.
I mean, if I could, I would still do integrals by hand, but I'll accept Python.
Yeah, I also don't have any experience.
Theorist at heart still.
What?
A theorist at heart still.
Yep.
I love it too. I love pencil and paper. I that's my favorite, but yeah. It takes
I'm
time.
adapting. Yeah, I'm adapting.
I think people who work on simulations, at least a few years ago, it used to be the case that for some simulation stuff, like you can do it much faster in C or C++ or even in Fortran than in Python. So
Yeah.
I think simulation people still use slightly older languages.
Yeah, I think there's a group at UC Davis that does simulations.
I'm starting second loop.
Okay, perfect. And this will be the last loop on the flipped pointing, and then we'll go to the 0 PA and finish off the night with that.
Okay. After this, next to go to the this should be.
So this would be the lattice. Can you go up to the targets?
Next target.
Yeah, so this would be lattice underscore D2, exactly that one. P2 backup.
It's backup, not flip one.
Sorry, can you repeat?
Sorry. That is to P2 backup PA equals 0, right?
Correct.
Next target.
Yeah, so after this loop, then we'll go over there.
Okay. After this loop.
Yeah, so Andrew Wetzel's group at UC Davis, I think all of the, near all of their programming is in C++. And they're all doing simulations. And yeah, I guess it's quite a bit faster, but there's a pretty big barrier there. I think for graduate students, they have to do a year of kind of wading through programming before they can actually get to some physics questions.
Yeah, and I think I don't know much about this, but there are also Python packages that you can download, and then they use C+ or C++ or Fortran, but you don't have to, write codes in C+. You can just write code in Python and use the package. So there can be also ways around learning C++. So
Yeah, doesn't pandas do that? I thought data frame, that's what data frame sees, but I'm not sure.
yeah, I don't know much about it.
Sorry, what's the question? I heard.
Yeah, I was wondering if pandas was like one of the packages of Python that use C++ in the background.
Okay, I don't know that. I just use the pandas a lot. So it's
Yeah.
a nice like package, like if you have a large data set.
Yeah, I used something recently that used C++ in the background to make one of my things go faster, but I don't remember what it was.
Hey Lou, have you noticed sometimes there are two windows for time to completion and both of them show slightly different values? Uh,
I
do you
think
know
why
why that?
one is for the blue, one is for the red band.
Yeah, but then it only shows up sometimes and not other. Like right now, I think for a
It's-
while I haven't seen two windows. Or is it there and
Yeah,
they just clicked on it?
I don't know.
Okay.
Exposure.
So Raja, I see there's the question about dark energy. Did you want to expound a little bit on the differences between dark matter and dark energy? Just to keep you awake.
I am having a hard time staying awake, so I think I
You can
will
also go to
pass
bed,
on that.
Raja. I know you've done this now 2 nights in a row and you have a meeting in
Yeah,
3
I think
hours.
I will pass on that. But let's see. Just want to make sure there's nothing specific for me. Well, thank you guys for hosting again tonight, and we'll be in contact, Brian.
Yeah, thank you, Raja, for coming again and supporting this and for making us part of it and everything. And yeah, it's really wonderful that we got a chance to do this with Subaru, and despite the technical issues. And yeah, let's talk sometime in the future
Definitely.
about expanding this.
Yeah, bye to all my friends, many friends. Take care. Bye.
Okay. Good night, Raja.
I quickly want to say, if I'm skipping your questions, I'm mostly missing it, but sometimes I also don't know the answer. So you can ask again, and I'll pass it along to somebody else.
So there was a question about whether we often use histograms. That's a pretty easy one. The answer is yes, absolutely. So there's all sorts of different ways to represent data. But for example, Lou is looking at our data right now. So it may look like we're doing nothing here, but we're taking pictures with the telescope and then Lou is analyzing them. And she's trying to get an understanding of how deep these images are relative to what we expect the depth to be, because we're looking at very, very distant galaxies and we're trying to understand, are we getting pictures that are deep enough to be able to detect these galaxies, at least to our expectation. And so one way that you can measure the depth of an image is by plotting a histogram of the brightnesses of the objects that you look at in the image. And when you start to see that histogram, so if you go, if we start off at very bright objects, there's not very many bright objects in a given image, and that number should increase as we go to fainter and fainter objects. And if we had an infinitely deep image, that would just keep expanding. So a histogram would just keep going higher and higher and higher as we're going to fainter and fainter brightnesses. And so that's that factor as the factor of the histogram increasing is Euclidean space. So that's some factor of, I forget what the actual exponent is. And so, but because we don't have infinite depth images, we'll see that histogram start to fall off. So there will be a part of that histogram where at a certain brightness, we no longer see as many objects as is the expectation from Euclidean math. And when we start to see that happening, that sets the depth of our image. And so this is just one example of the many, many examples where we would use histograms. But that's only one way of representing data. So we use scatter plots, we use three-dimensional shell diagrams, phase-space diagrams, all sorts of different ways of representing data. And each of them tell us a different thing.
Move the telescope. Start exposure.
So yeah, so there was a question about dark energy and what the nature of dark energy was. And so that's a great question. The answer is we don't really know what dark energy is at this point. We know its effects on the universe based on the motions of galaxies. So dark energy is the energy of the vacuum itself, and it has something called a negative pressure. So it repulses, it causes an anti-gravity movement for galaxies and everything else in the universe. So it's an actual stretching of space-time. And that's not to be confused with dark matter, which is unseen matter that's probably of a different nature than the kind of matter that we see, like what's called baryonic matter. So for example, humans or stars, that's all baryonic matter. And dark matter has gravitational influence, so it's not repulsive. It acts just like normal matter with gravity, but we can't see it. We can only see its effects. So both dark matter and dark energy, we can only see its effects and infer that it exists, but we can't measure it as of yet. Anyways, we can't measure it directly. So Raja, in Raja's honor, since he's no longer here, had a good pun last night to remember the difference between the two, which is that while dark matter sucks, dark energy is truly repulsive. So that one's for Raja.
That's dark.
It's dark, yeah, very dark. Lou, have you seen any sort of seeing estimate recently? I haven't been paying attention if they measure the seeing on the image.
No. You can ask them.
Yeah.
I
Yeah, I
don't
was just
see
wondering
any.
if you happen to notice. Hey, Andrew or Shuei, have you guys taken a seeing estimate recently?
Sorry?
Have you taken a seeing estimate recently?
I'm seeing?
Yeah.
Yeah. Oh, 0.5.
Okay. All right. So we're holding steady all night. Okay. I won't ask you anymore then, because I can clearly extrapolate that to the end of the night. That was good. Okay. Thank you, guys.
Hey, Brian.
Yeah.
So I'm estimate the depth, like rough.
Yeah.
This is from our first night, Hyperion pointing one.
Okay.
So it's
The
like
numbers you were sending me, they're like 23.4, 23.3.
three, I think.
Yeah, those are from the first pointing of Hyperion.
Yes.
Okay. And that was with 5 loops?
Yes.
Okay. So that's about 60-65% of our nominal depth based on an expectation of what it was 23.7 that we wanted.
23.8.
23.8. Okay.
So 0.5 difference.
So about 63% of our depth that we wanted, which would mean that we would need to do 8 pointings per field to get to our depth.
So it's better than what we expected.
Because we expected 9.
Yeah.
9 loops. Okay. Okay, but within the slop factor, that's probably, so we can probably count on doing 9, right?
Yeah, like 9 and 8 and 9 is like okay to fill up the full depth, to reach
Okay.
the full depth.
So if we just game this out for a second, so we've now, if we get through the 5 loops on here, then we will have 5 loops on each pointing. Is that right? Or did we get 6 last night for one of them?
We have 5 last night each.
Okay. And 5 on each pointing in the first night?
Yes.
Okay. So it'll be 5 across the board. So there'll be 5 loops on 6 pointings. And we would want to do 4 additional loops on each pointing to get the full depth.
Yeah. I think we just go 9 loops, because even if even we do 8, we probably don't have time to cover another one.
Yeah, I'm just even thinking, are we going to have enough time to do, assuming everything goes wonderfully? I mean, we're getting, so the first night we had really good conditions. I mean, we had, what, 0.35 arc second seeing or something like that. So it's only going to get worse from there. I mean, unless unless our luck really, really goes through the roof. So that depth is probably the best that we're going to get, that you estimated right there.
Yeah.
So
probably.
that means that 4 pointings is kind of the minimum or 4 loops per pointing is kind of the minimum to get to our nominal depth.
Yeah.
So are we gonna have enough time to do all 6 pointings at 4 loop depth in 2 half nights?
Probably. Yeah, around that. If everything go well.
So we've normally started at 1 o'clock in the morning, Hawaii time, right? And we finish up about 6. So we have 5 hours. So we have 10 hours total to work with.
Yes.
And you said every loop takes about 27 minutes, something like that.
So it's like half an hour.
So yeah, let's call it half an hour with the overheads. So that's already 12 hours, assuming that everything goes absolutely smoothly. So I think we do not have enough time to be able to go to full depth on all of the pointings.
Yeah,
So
yeah, I think.
we're gonna have to sacrifice something. So I think it makes the most sense to me if we're gonna end up sacrificing something to sacrifice the lattice structure, and not because it's less interesting scientifically, but rather because we've already had the prescience to flip the detector. And so because we have no images with the flip detector in Hyperion, if we just go, you know, a couple loops, we may not mitigate the detector defect enough. So I would tend to go for the Hyperion pointings of full depth, and then maybe go, what would it be, maybe 7 loop depth on the 2 lattice pointings, something like that.
Yeah, so we can do tomorrow for Hyperion and see what we have left for lattice the other day.
That sounds good.
The
Maybe we can drop those Hyperion loops to maybe 3, because we had such great conditions, at least pointing 1 and pointing 2. We had such great conditions the first night. So even if we get the conditions tonight, which are already really good, or maybe even in something a little bit worse, we can absorb only doing 8 loops in each one of those pointings. So let's see if we can shave off just a tiny bit of time.
Yeah, I think 8. 8 should be fine.
Because we save an hour if we do that. So if we do 3 loops in pointing 1, 3 loops in pointing 2, where we probably have the best data, at least we save an hour there. And then so maybe we can make up an hour somewhere else.
So we need to do 3 and 3 for 3 for pointing 1, 3 for pointing 2, and 4 for pointing 3, because we have like one loop, not full loop, like 5 data for the pointing 3. So I prefer to do 4 for pointing 3 and 4 for pointing 4. And like if like the last one we can do 3 or 4. It's not like just one loop. Because we so for pointing 4 we may have issue on like last minutes, that twilight.
So, sorry, one sec, Lou. I see that Pran's leaving. Pran, thank you very much for joining us and for organizing everything. We really appreciate it.
Thanks to all of you for answering all the questions. Yeah, I have to run. I've got class, but thanks a lot, and I hope to see you again soon in another session.
Yeah, we will definitely do this again. Thank you very much for making it a success.
Absolutely.
Yeah, sorry, Lou.
No, it's fine. Because the like 1 or 2 dither for the pointing 4 is already hit the twilight, so the data may not be that good.
Oh, okay. Yeah.
For that
so
pointing.
I think why don't we just plan for if things are okay, why don't you, if you don't mind, could you make like a plan, like let's say for kind of conditions like we have now, and then a plan if conditions are much worse than now, and then we can just follow that. So like two variations of the plan, one a contingency if things go really bad. But it sounds like if things are kind of okay, like we have conditions like we have tonight, then we could go 3 loops on pointing 1, pointing 2, 4 loops on pointing 3, pointing 4, And that would leave enough time for, let's see, what is that, 3 hours plus? So that would leave enough for 3 pointings, 3 loops on each pointing in lattice. So that's pretty good. So that would, I mean, that would give us, 8 loop depth, basically across the board.
Yeah.
Yeah. Okay. That sounds good to me, Lou.
Okay, I will make a plan for this, and like we can think how if doesn't go well. Okay.
No, but that's great, and thank you for getting the estimate so quickly. And was the data reduction fairly easy to do, or has it been a little bit complicated?
It's a little there are little issue because of the structure there.
Yeah.
But Masa from Swim's team, I think he wrote the pipeline and helped me a lot, like over the email for from last night to today. So
great.
we like solved the issue, and the output is great. And once it's solved, it's really easy to run it, like quick and easy. So it's really good. The pipeline is really very easy to use, and it's written in Python, so I can read.
There you go.
Yeah.
Yeah, and since you estimated the depth on the chip where the structure is, that actually, if you do it on the chip that there's no structure, assuming that it's just a sensitive, probably we'll get a little bit better depth there, just because there's a decent amount of attenuation from that defect.
Yeah, I will check that quickly once I done the other chip.
Great.
I'll let you know. Brian, we're on the last loop, last like dither.
Yeah, and so we're gonna flip after this. Yeah.
Yeah.
And so Lou, if I'm calculating right, it seems like we'll start to run over 12 degree if we do 3 loops here. So it may be that the last loop is not great because it'll start getting bright.
Yeah.
Just to keep in mind that loop may not be to full depth.
Yeah, it's okay to like finish the full loop, or we quit at some point.
Yeah.
I will always keep eye on the last like frames.
Okay, sounds good. So Shui, I think we're ready to go to the flipped, or I guess we're on the flips of the non-flip, so the PA0, same pointing. Correct. Yep, the one you have highlighted.
A mistake. This one. They set up this or lattice 2D.
Yep.
Move telescope.
And we'll do a quick exposure to verify the field, yeah, after the rotation.
Sorry?
We'll do a quick exposure to verify the field after the rotation. Is that correct?
I take a test exposure. I'm starting the first group.
Sorry, Shuaid, are you displaying the acquisition image in the VNC window, or is this the flip 180?
Sorry. Pardon?
To verify the field, are you displaying the acquisition image? It looks like it's the 180, flip 180.
Brian, I think it's right, but it just changed.
You think it's right, Lou?
Yeah.
It doesn't look right to me.
Not this window, the other window.
Which window are you looking at? There it is. Yes, that looks fine.
Fine, okay.
Yep.
Okay.
Yeah, the previous. Okay, that sounds great. Yeah, please do. Lou, the previous image was the flip 180 image, as far as I could tell.
Yeah, but the current one, like showing in another VNC window. The now
okay.
is the white one.
Okay, you
so
can see it there. Okay. I see what you were seeing. I got it. Okay. You're much more of an expert than me with swims.
Is it?
I feel like a novice here. So yeah, that's the live feed there. So in your screen at the top right. Yeah, we were doing it.
Yeah, it's live.
And that's so I guess what's being shown in the Jenga window is somewhat of a reduced image or something. Because there's a frame 1 and frame 2, so it's leaves a background subtracted image, something like that.
Yes, I think so.
Lou, there was a question directly to you by Blina. Blina asked, when you started working this job, what part was the hardest? if you have time to answer now. If you're doing something, no worries. Observations take priority.
No, it's fine. I just calculate the depth of the other chip. When started this job, you mean like the PhD or the postdoc? So I'm right now a postdoc. I think this is count as job.
I would say probably like your astronomy career, like maybe even like when you first started, like kind of doing research or something like that. I'm not totally sure of the question, but I'd probably like for somebody that's getting into research and astronomy, like what was the hardest part for you?
Yeah, I think, oh, okay, I think I can think one of them. So sometimes you got nobody know what you're doing. Like no one can answer your question. Like why reduce the astrology?
So yeah, Belina, it's there's a difference between astrology and astronomy. So we're astronomers, which means we take we're observational astronomers. So we take observations of the sky and try to interpret them in terms of the properties of the stars and galaxies and underlying matter and forces in the universe. Astrology is trying to read something into stars and then predict something about human beings. One is science. Astronomy is a science. Astrology is not a science. There's no verifiable fact in astrology. So there's a difference between those two things. Sorry, Lou, I just had to interject there.
Yeah, yeah, but I can answer that question. Is like it's hard to like nobody around you like really know how to solve your problem. So you may have problems like in your own analysis or reduction of the data, or like in the on the process of like any step of your science. So this is the hardest part. Like sometimes you just don't have people to talk to help you there. But hopefully that was for me that was solved. Like there are people not like in your own university, but a little bit away from you. I went to Netherlands to learn like data reduction, the radio data reduction, and then I come back and more confidence to do that by myself. So yeah, I think that's it. And when I moved from PhD to postdoc, I think the hardest thing is like in most of the case, for me also, like I also changed the field a little bit. So from my PhD, I'm doing radio. I'm working on radio galaxies and the environmental effect of galaxy evolution. But right now, I'm working more. Like my job is on AGN feedback. Not very similar to what I was doing before. So the change also, like I think is the hardest when I take the job and transfer to the postdoc job. Well, doing a project was your biggest mistake? Do you fix the mistake? Or did you ruin it? Or you yeah, there's I think it's kind of mistake. So I in the paper in the yeah.
Did you ever make mistakes in graduate school, Lou? I don't remember.
Yeah, I wrote one. So I have erratas. So it's when you publish a paper, and if you found there's a mistake in your analysis or any like or just the language in the paper, you wrote a erratus. Is it called erratus? I think.
Erratum,
Yeah.
Erratum to
Plural would
correct
be
for
errata.
errata. To correct for the mistake you made. So yeah, I have two errata. One is during the undergrad, for my first paper, there's a small error in the code, and I found that like a little after the paper was published. So I wrote erratum afterward. And also I have another one, like just recent. So the error is just it's in the paper, like a language issue, like a typo, but we decided to make a errata to correct for that as well.
But
Did you
you're not alone in this. So I mean, this is like, astronomy is very hard. I mean, there's tons of moving parts in astronomy. You know, again, you have to, you know, propose for observations. You have to have ideas. You have to then prepare for those observations, take those observations. You have to have help taking those observations. So, for example, we have people on the summit of Mauna Kea tonight helping us with those observations. They're at 13,700 feet. And so there's not a lot, there's about 60% of the oxygen that we have at sea level up there. And so, you know, you get lightheaded, and so it's easy to make mistakes. I mean, already it's, you know, 4:54 in the morning here, lack of oxygen, lack of sleep, very easy to make mistakes during that time. Then you have to analyze all those data, and then you have to publish things, and even just, you know, writing a word wrong can lead to an erratum. But this is why you have a team that works together. And so Lou knows about this, that we did a lot of teamwork together to make sure that each, as best as we could, that we supported each other and made sure that, you know, we were doing things in a way that we all thought was right. But if you're not making mistakes in astronomy, you are not trying. If you're not making mistakes in doing science, you're definitely not trying. You're playing it safe, and playing it safe is not really doing science. And so you want to make mistakes, because that shows you're at the edge of your comprehension, the edge of your abilities, and you're always pushing those things forward to challenge yourself. I am an avid skier, so when I go out skiing, if I do not fall once per day, I am not trying. I'm not challenging myself, and that I really hold to that. So if I'm on my last run of the day and I haven't fallen that day, I'm really pushing myself hard. And probably Lou's seen a few of those falls. So yeah, so everybody makes mistakes, and it doesn't ruin things. I mean, they can be very bad, but it doesn't ruin things, and you can always come back and reevaluate. Or worst comes to worst, you publish an erratum. So you don't do something like this living in fear that you're going to make a mistake. You embrace those mistakes and you learn from them.
Thank you, Brian.
なんでしょ
像が、像ちょっと似てるんやけど、そう。I'm checking the image quality. It seems that the EFX looks a bit elongated. Its direction. So, right.
You guys want to focus?
I'm not sure. Yeah, this doesn't usually happen. So this may be some astigmatism or sort of optics, I suppose. Actually, I'm not sure how we can deal with it. Yeah, probably part of this will be related to the mirror analysis of the telescope. And but I think this is obviously astigmatism. Yeah, incomplete telescope mirror surface.
Exposure.
Yeah, it seems that there's a 3-pixel offset between the photop max X and Y. That's what you're seeing?
Right.
Yeah.
Yeah.
But a focusing wouldn't fix that, you don't think?
I think if we do some focusing, we may have some improved image quality, but I'm not sure which direction should we move for chasing focus.
Yeah.
Probably. So the current short value is 0.7. All right. So considering the trend, yeah, we may just change the focus a little bit and see what's going to happen. That's my suggestion. I suggest to go towards positive value. So it's now 0.07. So I think we better try 0.05. and see what's gonna happen there. Yeah, so, yeah, Shuhei, I think we better change the focus anyway.
Okay.
No, it's the chance. 4.05, minus 4.05.
Is that a pretty minimal change? The 0.02
Yeah,
change?
very, very small.
Yeah.
Very small, so it won't do any disastrous thing.
Yeah, and so we'll just kind of see if it trends in the right direction.
Yeah.
Yeah, that sounds good.
Just just take one image, and then if something goes wrong, we can go back to the original position after that.
Okay, sounds good.
Just be open.
Thank you guys for monitoring that.
There was no problem.
And
Brian,
Lou,
is this
the estimate right now is 0.7 arc seconds, but there's a decent amount of astigmatism. So there's a, let's see, about a 3 pixel offset between the full width half max and the X direction and Y direction.
okay?
We're
Is
getting
it
about
is that
9
all on
pixels.
3 or loop 4? Loop 3, right?
This would be
8.8 and 6.0. Yeah.
This would be the first loop of the flip, so it would be the third loop. And yeah, so we're getting 8.8 in full width half max X and 6.0 in full width half max Y. And you can see on that in the image that you're sharing in the top left. It just went away, but it'll come back. That there's definite elongation there. So we're going to move the focus a little bit and see if that improves things.
Can it do like focusing when like taking exposure or change the focusing?
Yeah, I'm guessing they have a focus loop. Yeah, of course. So in between exposures, changing the focus, or even while you're exposing, changing the focus, a small focus move is not going to change things.
Sorry, it's the direction.
No, it's worth a try. Okay.
Yeah.
Yeah.
So we should go to 0.09.
Yeah, but that's good. That's a decent change. So that's good. All right. So we just it got worse, but it is changing.
Yeah, 0.09. Okay.
So we just picked the wrong direction.
It's playing around with the focus.
So you might want to make a note, Lou, in that frame that we just changed the focus. So it went from minus 0.07 to minus 0.05. And now we're going to go the same magnitude, but the other direction. So to 0.09,
Okay.
minus 0.09. Lou, in the chat, there was a question if you could just enlarge the top left screen so that people could see the astigmatism.
Top left.
今って星が横に伸びていって、で、一応、どっちに動かしたの最初。最初は、プラスに動かせますか。プラスで、プラスにあると、悪化した。悪化した。わかりました。そうです。ウィキにメモを残して。
Exposure.
Let's see.
Sorry. So probably doing it wrong. For this spring, limit will be worse than before afterwards. So,
Yeah.
so I was wrong there. I think we do a back and forth thing. So let's try 0.05 minus 0.05.
Is there some sort of like hysteresis in this?
Yeah, this is the recent one, most recent one, and it gets worse after 14/7.
Yeah.
I'm not sure what's going on. Yeah, the temperature hasn't changed so much, right?
Mm-hmm.
Several hours, 2 hours. A bit decreasing still. We had some change in humidity, but it's not much actually.
Yeah, it doesn't look like it.
Minor, yeah. See anyway.
Hey Lou, what
Yes.
does nread_b and nread_r mean?
Where should I look?
Oh, that's the line they are currently executing, the main get object line. That's highlighted.
This one?
The one that is highlighted. Yeah, yeah. So you can see nread_b and nread.
That's the read. Brian, I don't really know.
My guess is it's the number of exposures in the blue channel and the red channel. So it looks like that there's
No, the
I'm definitely
read.
not.
No, we
No,
already
and-
have an exposure.
Okay, so this is you don't these are non-destructive reads, so it's clocking the CCD and kind of getting I think it says Fowler sampling, so mode equals Fowler. So Fowler sampling on a infrared detector, it's just a kind of sampling. So you're just kind of checking the charge as you go along. And so it's just reading as it goes along and then kind of extrapolating out. And so it's one clever way of getting the charge there without actually doing a destructive read where you actually read out everything.
I see.
We have the same thing with Mossfire. It's the
Yeah.
same. I forget I think it is called number of reads or something like that.
Yeah. I think the only thing I know is the nread will like if it is large, like also increase the time for like readout.
Exactly. Yep. Yeah, because you kind of have to pause things as you're reading them. So yeah.
Okay, it looks better. Overall theme is not so good actually.
Yeah, it looks like it's degraded quite a bit.
7 to 9. So different. So
May I ask what you did differently this time? Is it, what's the focus value?
it's now minus 0.05. So we increased the focus value.
And so that was our first move, right? It was because it was minus 0.07 and then we went to minus 0.05.
Yes, yes.
But it seems to have solved the problem this time, whereas it didn't solve it last time.
I'm not sure it's, I'm not sure it's a bit kind of a unstable behavior, and I'm not sure what's going on actually. Yeah, sorry. So, whether we should put into another change or.
I think so, yeah. I would be comfortable with that.
Okay. Right, then let's go to minus 0.03 then next for the next exposure.
That sounds good. Lou, are you kind of monitoring the astigmatism here?
Yeah.
Yeah.
So they're doing measurements of the astigmatism, and you can see here
Minus 4.03.
it's it looks like it's getting quite a bit better, but
Yeah. But I heard you guys decided to go a little bit further.
yep, exactly. Yeah, we're gonna cowboy it a little bit. So we'll see whether that makes things better, because it looks like there's still about a 20% astigmatism.
Yeah. Thank you.
But there seems to be some hysteresis here. So this is that the value that's chosen here is actually the same as our first move, which made it worse. So, but it's not uncommon to have hysteresis in optics.
Yeah, I see they also changed the subtracted frame.
Yeah, probably that. Well, yeah, that probably wouldn't matter too much because they're doing a positive image here.
Yeah. I think it's getting better.
Yeah, hopefully. But the seeing is getting worse in general, so I think we're up to.
It's 0.6.
Okay.
Actually, yeah.
Not too bad.
Not too bad. Yesterday is also at this time it's 0.7.
Exposure.
Looks like the wind speed is holding pretty steady, so it's a bit interesting. Seeing. Actually, dim is returning better value now than an hour ago.
Yeah.
Lou, I think there was a question or a request in the chat to make the. Yep, you're ahead of me. Thanks, Lou.
There's still some astigmatism.
Move to the the telescope.
Right, I think we end this loop.
Yeah. Jue, you're gonna start another loop now?
Okay. One loop.
Great, thank you. Lou, I'll be right back.
Got it.
Lou, do you have a minute?
Yeah, go ahead.
Could you help me understand the timings? So for each dither, we are taking 150 seconds of blue and then 70 times 2. So that's 140 seconds of red exposures, right?
Yeah.
So that's 290 seconds because 150 and then 140. So that's 290 seconds for each dither. And then we are taking 9 dithers. So that's already like if you do 190 times
I lost, but I can explain from the beginning. So let's just try for the blue band. The blue band is 150 second for each dither.
Right.
And then we have 9 dither pattern, number of dither. So 150 times 9, and you're gonna divide that by 60 to get minutes. So this is second. Yeah, this is 22.5 minutes.
Right.
Right. This is for the blue.
Right.
And you're asking like for the right part. So this is the swim is simultaneously get 2 band.
Oh, okay. That's what I was missing. That makes sense. Yeah, because I added
You're
them.
not adding 22 to 22. You're 22. The other is simultaneously.
I see. So then how are you calculating overall exposure time for the source? So do you just use like one of them, or do you just take like for however long we were on that source? Because in your email, I think you mentioned number about like total disintegration time on a given source.
Yeah, so I think you're asking how I decide the total exposure time for that like magnitude.
Okay, it sounds fine.
Let us try just one more push.
Okay, no, that's great. I'm happy to push it. Yeah, please.
Okay, I see they're changing to the focus changed to -0.01.
Yep, that's right. Yeah, we're gonna keep pushing. It looks like it's improving things. So, yeah.
No, the value is almost same actually, but we still have elongation toward the diagonal direction. Yeah, let us try another one.
Yep.
I suppose this works.
Okay, thank you.
You're welcome.
Acta. So the depth is depend on like depend on like the O2 emission, like the limit of the O2 emission. So here we got the narrow band is a small like range in the like broadband. So what you actually do is take a subtraction from the broadband and the narrowband. So you get anything left is basically the O2 emission. So what I do is I have the broadband depth. So I assume one narrowband depth. So I subtract them and calculate the O2 emission.
Oh, very good. Yes. Okay. Nice job, guys. Thank you.
Yeah, we should have noticed much earlier.
Okay.
Yeah.
I'm glad you got it.
So when you get the, like, does that make sense to you? Like,
Yeah, no, I get that. I'm wondering, like, right now. So right now you said that it takes both blue and red observations simultaneously, right? So so in that case, so for given dither, do you consider the exposure time to be 70 times 2, so like 140? I guess both of them are equivalent, right? One is 140 and one is 150. So do you just use that value and then you multiply that by like 9 dither patterns and then how many loops we are taking? Is it how you are calculating the integration time for the whole sources? Or do you add the integration time of blue and red together? When you mentioned like the final number in the email, how are you calculating that?
So for the exposure time for each frame, this is taken from the same as Morix that we used before, and that's Brian decided that. So I just took that the same. I didn't change that for the narrowband. The Morix study is also using a narrowband. So, but in a little bit like brighter, like near infrared. But basically it should like same. So the same. But this exposure time, the thing you want to make sure is that like in each frame, the stars is not saturated. So as long as it's not saturated, you can also always push that to like a larger number. It's okay. And also if it is longer, there's a like background, it will be higher, I think. So you kind of have to think about that too, because you take a long exposure, the background will also be higher. So for the medium band, the right band is 70 seconds. It's just because it's a broadband, we don't want to take long exposure on that to get saturated on the stars, and the background will also be like the same reason. Because the filter is wider, so you get light more. So that's how you decided. That makes sense?
Okay. Yeah, thanks so much. So in some ways it would be right to say, like if we observe this source for an hour, it will be like 1 hour integration time in blue and then 1 hour integration time in red. So in some ways we have like 2 hour time on the source, right? Because you're using different filters, but overall you have like 2 hours of observations for the source, right?
Yeah, you can think that way.
Yeah, that's cool that it can take both of them simultaneously.
Yeah, this is the like advantage of swim.
Is it only two, or like what's the upper limit? Like how many filters can you use simultaneously? Do you know?
For swims, only two.
Two? Okay.
Start exposure.
So I think I might have missed this, but for tomorrow, are we taking observations of both flipped and unflipped version?
Yes, we took flip and non-flip, like original, because there's a structure in the narrowband. So if we flip 180, it will go on the other side. So hopefully we'll, after combining all the image, it will average out.
Right. Okay.
Shui, can I ask you a favor? So on our next couple of nights, we're gonna do a 180 flip of the pointings that we've already observed on the previous nights. And I was wondering if you could just update the OPE file now, so that we could have those ready for the next.
Yeah.
So I can tell you which pointings those are. If you scroll up in the OPE file, I can tell you which ones they are.
Start exposure.
So this should be Hyperion 1 through 4.
Hyperion 1.
So 1, 2, 3, and 4.
1, 2, 3, and 4.
And so yeah, we just like to flip each one of those by 180. Lou, did you rename these? Like because I remember the changed Hyperion pointings were like backup or something like that, but these are the correct ones, right?
Yeah, this is the correct one.
Okay.
So I removed the backup.
Yeah, okay. I figured you would have corrected me if I was saying something silly.
Telescope. Start exposure. Start exposure.
So yeah, this also means we're not gonna target AOS, the second peak, right? That's 0.5, if I remember right.
Sorry, I didn't get
So
it.
like 0.5 was the second most massive peak of Hyperion. It was 0.5.
Yeah.
Is that right?
Yeah.
So that means we're gonna completely.
The lower one.
Yeah. Okay.
Mhm.
Oh, we should have applied to swims for 22A. We'll have to do that again for 22B because yeah, I think we're leaving a lot of stuff undone. And I'm really curious to see what happens with the data and the lattice structure. And I'm guessing we can actually go after other lattice structures with swims.
Yeah. I hope yeah, we have one more chance. If we propose for same time next year.
Yeah, and then swims is going off the telescope after that, and Marks is being put back on.
But Morx will put back on after a year.
A year after swims comes off.
Yes.
What's happening in the interim between those two? Do you know?
No idea. And I think when Morix back, it's not the spring Morix.
No. They need
Yeah.
ground layer adaptive optics for that, which I was just talking with Ichi, and I think that's 5 years before they're going to have that ready, and they still need quite a bit of funding, so several $1 million before they're going to be able to really get that off the ground. So it looks like an amazing instrument, absolutely amazing. So I think he said the field of view was like something like 16 by 16 arc minutes, and then it's going to deliver with the ground layer adaptive optics. It's going to deliver like 0.2 arc second image quality across that entire field of view.
That's really nice.
So I mean, you're almost at Hubble resolution there over a field of view, which is, I mean, Hubble, what is like with C3 is like 1.5 arc minutes on its side. It's a rectangle, but something like that. So I mean, even W first is like not even close to that big.
Well, it takes time.
Yeah, nobody to my knowledge has ground layer adaptive optics going yet, and Gemini is also working towards that.
BLT has a adapted optic AO.
Yeah, they have the next generation AO, like from Muse. So they have these like 4 lasers, but I don't think it's ground layer. If I'm not an adaptive optics expert, but I don't think they take care of the ground layer. The ground layer is really tough, and that's actually where most of the seeing bubbles come from. So To my knowledge that, I mean, there's prototypes out there, but to my knowledge, that hasn't been developed in any operational capacity yet.
Okay. I only know that the one at VLA for me. Not the
Hawkeye. Okay.
Yeah, but I'm not sure what's going on with it. You know, yeah, I heard that they're working on it, but I'm not sure. Yeah, what's the result they got so far?
Hawkeye is on one of the BLT telescopes, right?
Yeah, that's right. Yeah, they have a adaptive secondary mirror. But yeah, really, yeah, Subaru is also curious about what's going on for the Galileo and VLT.
Yeah.
But yeah, so far we're not sure much about it.
Yeah, I think Gemini is as well.
I see.
Yeah, they hired Christoph from Subaru to work on Christoph Plejon.
Oh yeah, that's right.
Now at Gemini, yeah. So he started the same day that I started at Gemini. And
oh really?
Yeah, exactly. Yeah, we got training together and everything. And yeah, so I think they're starting to ramp that up, but I think they have some money for it, but not enough people at this point yet. I guess
really, yeah, but
I think it's really hard.
Yeah,
yeah, I think it's really hard to find good people for that.
Yeah, that's right.
I know Subaru does have some plans for ground level AO with ultimate.
Yes, that's right. Yeah.
Don't know much about that, unfortunately, but.
Yeah, actually, no, Inoue-san is working for the adaptive secondary mirror system, and yeah, the problem is, we also need a laser guide star system as well. We have to launch at least 4 of them. Yeah, so it's a very challenging thing to do.
Yeah.
But the good news for Subaru is we just funded for 10-year fund for next 10-year operation. And that includes the development of the adaptive secondary mirror as well.
Great.
We hope we can do something. Yeah.
Is that the next budget?
Yeah, that's right. Next budget.
Okay.
That's the Subaru 2 project.
Yes, yeah.
So Andrew, what time do you have to leave the summit tonight?
Let me double check. It'll be around 7:15. But we'll be getting the exact time.
So Lou, I guess we're getting pretty close to the last exposures on this loop. It looks like we'll hit just about 12 degree if we do one more loop. Hello.
Yeah, 7:16. Yeah.
Yes.
Calibrations this morning.
Maybe flat, some flat, or narrow band.
I think so because we have it says 1292. We're using
random
1526.
Will this be imaging or spectra?
Yeah, imaging.
Okay.
So maybe
yeah, so for the top screen.
Yeah, okay.
Yeah.
Hey, Lou.
Yes.
1 second. Do you have a minute?
Yeah.
The screen that's like on your rightmost, that's kind of hidden at the other screen, that's the one where they show live feed, right? That's the live feed one? Yeah.
This is the live.
So why does the pattern only, like if you look at last two images over there, it just changed. Okay, I guess last three images. So you can see, it keeps changing. Okay, you can see that kind of structure on one of them, but then not in the other. Why does it disappear even though like both of them are blue frames, you know?
Yeah, so that's the like a structure we call structure in the blue blue band. So this is the reason we flip it.
But then why is it not there in the other frame? Oh, that's the flipped one? Is that the flipped one?
No, the other one is red. I think doesn't have that. The red band doesn't have the problem. It's only the blue band.
No, even the blue band, if you look at the one that's like in the middle, second from last.
There are two chips. The structure is only one on one of the chip.
I see. That makes sense. Okay.
Lou, we just got a seeing estimate of about 0.55, so you know.
Okay, I think we can go another one. Fine.
Oh yeah, definitely. We wouldn't want to waste this time. We just hit 18 degree, so. Unless you want to look for Messier objects, I say we continue with our serious science.
So are we observing both chips in blue and red?
Don't worry, we'll make a pretty picture of this one, Andrew.
Yes, so it's a simultaneously.
We'll do one more loop here. Same thing.
I think that's the one for swing. Simultaneously.
Yep.
Okay, thanks, Lou. And is the lattice, in your email, I see lattice P1 backup and lattice P2 backup.
Yes.
Is that the two chips you're talking about?
No. I'm talking about, hold on. Let me see.
Standard star?
No, we're gonna forego standard start tonight. We don't need it.
Yeah, you can see it here.
Did you guys have to take a standard for the first time?
This is a full field of view of swims. So it's 0.3 by 0.6 arc second. And there's
yeah, we're in the
one of them is 3.3 times 3.3. So this is a box here. And the other
No,
is
I
also.
can't hear you.
Thank you for asking.
You can hear me?
Okay, sorry, I couldn't hear you over the other talk.
Oh, okay.
Can you please say it again?
So can you see the big VNC I'm doing right now? So this is the full whole field of view of the swims.
Mm-hmm.
It's 6.6 times 3.3 times 6.6.
Mm-hmm.
And there are two CCD, like we call it two chips.
I see. Okay.
On the full field. So one of them, like this one, and there's this chip. This is chip 1, and on the right, and chip 2 on the left.
Okay.
And so this is only the showing up figure is for blue band, so it's a narrow band image, and it simultaneously will observe red band. We use H3 in red.
Okay.
And the structure is only showing on the blue band and on chip 1.
Okay. I see. That makes sense.
But we see structure in all of the chips, right? So I mean, like even though when we're looking at in the mainframe here, sorry, in the rightmost screen, we see structure there as well, but that's more fringing and other properties of the optics rather than the defect that we're seeing in the actual detector on the chip you guys were talking about. So there's different things going on here. One's an actual physical problem with the detector. Another one has to do with how the photons interact with the detector.
Okay, thank you.
But yeah, you could be tricked into thinking the sky has some sort of like wavy pattern, or I mean, those images look really beautiful. It's like, you know, I don't know, like blown sand or something like that, but it's kind of a pain in the butt to, to get out of the images because the sky doesn't actually look like that.
Brian, do you want to see the image from the first night?
Yeah, sure. Love to.
Exposure.
So these are the first two pointings. This is the blue band, or?
Yeah, so this is the blue band, the narrow band. Chip 2 on the left and chip 1 on the right. So you kind of see the structure here. Can you see a little bit here?
Yeah, it's almost like somebody's taking a bite out of the images.
Yeah. But it looks really great.
It does, yeah. Yeah,
and
the
fringing's
good.
Yeah, the swims also have a smaller pixel scale than the modes also.
What's the plate scale?
The 0.1.
0.1. And we were getting like, yeah, 0.35 arcs second seeing.
Yeah.
So it's good that we're getting 0.1 pixel scale. Otherwise, if the seeing, yeah, if it was like let's see, 0.15, 0.2 pixels, it would not be sampled well enough to reconstruct the PSF.
Hey guys, can you help me understand what I'm looking at? Am I looking at the region that doesn't look like have any stars? That in this image? Like, what did you look at and you were like, oh, it looks like somebody's taking a bite out of it? Was it the empty part?
Yeah, the empty part. So like on the right, well, so I see it there, I think, unless I'm convincing myself of something. But I mean, you see there's like structure in the right image, like kind of where Lou's mouth is now, just a second ago. It just looks like that there's something missing there, that there's the background has changed a little bit.
Okay.
And
yeah,
you kind of see it, the dead spot. There's things that look like they should be brighter there, and kind of fuzzed out and just kind of weakly coming through. And so that's because of the detector defect. And again, like, I mean, yeah, you can even see the background. Like, I wish I could control the mouse, but you see the kind of, there's the 2 stars exactly where Lou's just pointing there a second ago. Yeah, exactly there. You see, I mean, it's obvious the background has changed quite a bit there, and that's just because the pixels are dead. And so had we been able to dither over that, it would have medianed it out and it would have been fine. But our dither pattern was purposely smaller than the feature. And so it exists there still. So if we don't flip, let's say something goes disastrously wrong, heaven forbid something goes disastrously wrong tomorrow night or the next night, that's going to be in our image, and there's going to be artificial it's going to be artificially shallow there. And so let's say that, you know, structure magically ended up appearing there. Heaven forbid again. Yeah, you did good, Lou. It's not your fault.
No,
I'm not making any value judgments here. But
Yeah.
let's just say it did, then we would miss it just by virtue of this detector defect, and that would be sad. But you know, that's only what, you know, 20 arc seconds, 30 arc seconds, and the structure is supposed to be arc minutes large. So this is not, I mean, if the structure is there, we should see it irrespective of this, but we can do better than this.
Okay, thank you.
But yeah, if you look at the left image, you don't see anything like that. You don't see any like non-uniformity in the background or anything like that. You see towards the periphery because we've dithered that there's much more noise there. But and so you see, like, had we made our dither pattern bigger, like let's say we made it 40 arc seconds instead of 20 arc seconds, that border would have pushed in even further. So so we would dither over this artifact, but at the expense of, you know, probably another 10 or 20% of our field of view having higher noise.
I see.
So nothing comes for free, unfortunately.
Yeah, this is really cool. Oh,
I just want to say something. Oh, sorry. I just want to say something quickly. If you look at the live images screen, you can see a line on the middle image.
Yeah.
No, the live one, the Subaru. I mean the current one. Yeah. There, and then the one below that.
Oh, yeah.
So I think that's, do you guys think that's like cosmic ray or a satellite or something? I think
Elon
it's probably
Musk.
satellite, right?
That's Elon
Satellite.
Musk.
Yeah, because it's too long exposure to be cosmic.
Yeah, I don't think it's cosmic ray, and no, I think that's a satellite streaking through.
Exposure.
Luckily, we've taken like, I don't know, 50 pictures of this part of the sky now, so we can deal with that in image processing. But yeah, now we're getting close to sunrise. This is when we start to see these things. So Lou, can I ask you a provocative question?
Yep.
How soon before we might be able to tell if there's a structure there, do you think?
You mean the lattice?
Yeah, so I'm pretty sure there, unless I'm really wrong, and I've been really wrong for 4 years, I'm pretty sure there's a structure in Hyperion. And if not, then we've wasted a lot of telescope time. But no, we know it's there because of the Mossfire data and everything. So yeah, the lattice one. So, and I think it's really neat actually that we have like a verified structure that we're taking observations of already. And we can kind of compare like number counts of O2 emitters in those fields versus the one here?
Okay, it depends how hard I work on this.
Yeah, yeah.
It should be very easier because the coding are the same as like for Morix.
Yeah, exactly.
So when I like reduce all the data, it took me like later time to get like result out. I will try my best to get it as soon as possible. Like once we finish all the observing, or maybe just today's.
Yeah, I know you're very fast with this stuff, Lou. And yeah, it seemed like, I mean, once you have the photometry, which I mean, that calibrating that's going to be basically the same as what you did with Morix, then everything is the same, right? Like, I mean, you're just doing H band minus H3 or H band minus this narrow band, right?
Yeah, narrowband, I think is it J?
What is it? 13.
1360.
1360, something like that. Oh yeah, okay. So yeah, probably maybe H and H plus J or just J.
Yeah.
Yeah. I wonder, like, because I mean, unfortunately, we don't have like number counts from a blank field. So what would be really great to have like a number counts from a blank field, number counts from like the richest parts of Hyperion, and then see where the lattice structure lies in that spectrum. I wonder if there's archival observations of swims. I guess not, because we're the first to take it. We're the first to take observations of swims, I think.
So let me think. So right now I will have the yeah, I can there's nothing detected in MOSFET, right?
There was one galaxy detected in Mossfire at the redshift of it was 2.56. Was the
oh, okay, yeah, that's the
lattice
right
structure. The 2.44 that you mentioned earlier, that's Hyperion in the foreground.
Yeah.
So we actually discovered, we didn't discover the lattice structure, but we discovered that Hyperion goes on further than we thought it did.
Okay. Yeah, I can try like as soon as possible. And get the O2 emitter. Yeah.
Yeah, no hurry. Just curious. And I'm also like kind of curious how we might. I was kind of just like trying to brainstorm it how we might determine whether there's a structure there or not, because we basically don't have a blank field by design.
Yes.
I guess it doesn't really matter, because it's, number counts are number counts. So it doesn't matter whether we're using swims or Morix or whatever. So, I mean, we can do a comparison between like a field survey with, let's say, Morix or another instrument. Look at the O2 numbers around redshift 2.5, like expectations of number per co-moving volume, and then see if by how much we exceed or not in these fields. I mean, clearly in Hyperion, we should be exceeding it by a lot. Otherwise, something is wrong with the data analysis. So that's a good point of reference. And I think there are field surveys of O2 emitters at redshift 2.5. I forget which instruments have them, but I know we've looked at them before.
Yeah, I think I come and yeah, I think all the Morix like the published paper is something I can see. What I saw is all about like structures, like protoclusters or clusters.
Well, there was this like Heisel survey. I think David Sobral was running it. I think that's the survey, and that was done with UCURT with WIFCam, and it had like a narrowband component to it, and they were getting O2, O3, and maybe H alpha emitters at different redshifts. They might even be getting C3 emitters as well. And that was all like, yeah, like narrowband field kind of stuff. Let's see, I'm looking them up right now.
Move telescope. Exposure.
Yeah, so it was O2, O3, and H alpha emitters at redshift 2.23. So that's not exactly our redshift, but fairly close.
What's the name for the survey?
It's called Heisels. I'll put it in the chat. So even on their homepage, they have like number count.
Yeah, I think I have seen this website before.
Oh, Sobral wasn't running it. It was Best and Smale. But yeah, they've been pretty prolific in their publications. So there's some good information there.
Exposure.
So do we use a specific value of relative number density to say whether or not there is a structure?
Say it again, Ekta.
Oh, I'm just wondering if we use a specific value of like specific threshold for number density to say whether or not there is a structure, like a relative number density compared to, I guess, background or something. How are we finding whether or not there is a structure?
Yeah, so that was kind of the nature of my question. I mean, we know how to do it in like the Voronoi Monte Carlo sense, right? Like, I mean, this is we've done so many tests with Denise about trying to figure out exactly what kind of threshold we would consider something a structure, and then how we tie that to the overall mass of the structure and everything through simulations. Here, I'm a little bit out of my element, so I was trying to brainstorm as to like what we might do. And so, I mean, my initial thought is we take a field survey and we have the median value of like the O2 number density, and then we have the 1 sigma uncertainty, right? So that kind of gives you the field. There's of course astrophysical variance encoded in that uncertainty, but supposing it's just averaged over a bunch of field regions, then probably, I mean, protoclusters, protogroups, clusters and groups are very rare. So probably the dominant source of error there is the random. And so we have that, and then we have like our number counts in Hyperion. So like, for example, in Theia, like the center of Theia, which is the main peak, it should be very rich. We've seen that in the Mossfire data. It's very, very rich. Like, not compared to a cluster, but there's a lot of galaxies there. And so we kind of have the extrema set by the lower 1 sigma envelope of the field, and then what we see in Hyperion, right? And so then we try to figure out, where does this structure lie, or this potential structure, or let's say this structure as traced by the neutral cool hydrogen gas, where does this lie in terms of its galaxy richness relative to those two extrema?
And so for Hyperion,
that's my just initial thought.
So for Hyperion, let's say, if you choose some measure, let's say again, relative number density or something, you see, let's say the density is like 4 times higher or something. So I'm curious, does the same kind of ratio, do you also see same kind of ratio if you just use O2 detected galaxies? Like, I don't know what fraction of galaxies will have strong O2 emissions, and that will also depend on your depth and all, but I'm just curious. Does that question make sense? So let's say if I use, all different observations and not just, narrow band and this kind of imaging, and I see a lot of galaxies, and based on that, if I define number density, then I see 4 times higher number density. But right now I have used all different kinds of filters. So now if I just use O2, then let's say only, like some percentage of overall galaxies is emitting O2. So like, do you still see that's kind of over density, or is it like higher or is it lower? Because that will also depend on, like, if
Yeah. No,
I'm just thinking out loudly, like if you have like denser environment, how does that affect O2? So like, if that has some kind of effect, then you might see a different ratio in the over density if you just use O2 versus if you use all different kind of filters, right? Does that make sense?
No, it totally makes sense. And yeah, very astute observation and question. And yeah, these are all, I mean, it's degenerate. You can't, I mean, a priori, I can't answer that question, right? Because it's the question we're trying to answer in part.
Yeah.
And with these observations. So, I mean, as you say, there's going to be very likely a modulation of the, let's say, the frequency and strength at which O2 is emitted by galaxies based on the structure. So an older structure where galaxies are less star forming, if we say that the O2 line is a proxy for star formation, then we would see less O2 emitters. But O2 can also come from shocks and AGN activity, black hole activity. And so there's other reasons why O2 might be emitted, but we also have H beta O3 in the medium band filter. So we should be able to mitigate that some. But yeah, I mean, one of the suppositions by Drew Newman, who discovered this structure, is that the galaxies in these structures are more red, more dusty. And if attenuation goes as lambda to the 4th, then we're looking at O2, which is fairly blue. It would be attenuated much more strongly than something like H alpha. So we would be looking at the wrong line. But unfortunately, we can't look at H alpha. We'd love to look at H alpha, but we can't. So yeah, I don't know. I mean, this is the part of the adventure, part of the roller coaster of these observations, and I don't know the answer to that. I think we can get an idea of like variance if we look, from Hyperion structure to Hyperion structure. We know some of the properties of the Hyperion structures in terms of their virialization state and their masses and things. So we may be able to kind of back that out, but I think this is going to be a very long question, very complicated question, and we may not be able to answer it with these observations, honestly.
But definitely the Hyperion observations will tell a lot. So I'm pretty excited for that.
Yeah, it's a good control for sure. And the fact that we have MOSFER data as well, I think really helps. And again, we're going to have HST data as well, so which has O2. So I think we will eventually be able to back this out with the power of all these wonderful observations. But I think just with the SWIMS observations alone, we're only going to get a taste of of a larger picture. And I think we're on our last exposure for the evening.
Yeah, I think so.
Which is good because I think the sun's about to come out in about a half hour. So that was our last exposure that just completed?
Yeah, all done.
All done. Great.
Finish?
Yeah, we have nothing left to do. Is that right, Lou?
Yeah, that's right.
No reason to take a standard.
We need calibration. We need calibration.
A standard star?
No, calibration. The dome flat.
Dome flats?
Dome flat.
Yeah, so we'll take dome flats, I guess.
Okay, so close the dome.
Okay, close.
Yeah.
Okay, thanks, guys.
Thank you. So the dome flat, because the narrowband didn't have flat available online. There are a bunch of available flat and like dark image over online, like, but not the narrowband. So I need to take that.
Okay, that sounds good.
Make the flat ourselves.
Do we also need calibrations for the flip mask?
It doesn't matter. We just need the flat for the CCD.
Yeah. So there's a property of the detector, so it doesn't matter that we flip the instrument. It's still the detector is the detector.
All right. Yeah.
So it doesn't care where it's pointing in the sky. Okay, well, I think that probably can conclude the Shadow the Scientist portion of the night. We're done with our astronomical observations, and we're just going to take some calibrations now with the telescope dome closed. And I think a lot of the scientists are getting tired on this call, so we'll probably call it a night here. But thank you, everybody who's still stuck with us through this call, for joining and for asking all these wonderful questions and for following along with our observations. And this event will continue. Raja, who was on the call earlier, will have some nights in February on the Keck telescope and the Lick telescope, which is on Mauna Kea and Mount Hamilton in California, respectively. So look out for emails from Ohana Kilahoku for events coming up in February. There will also be promotions on Twitter and elsewhere. And I think that's it. So thank you all for joining us, and thank you to everybody on my team for helping to answer questions and have all these wonderful discussions. And on top of that, great observations. Yay.
Oh, I was muted. I did say yay.
Okay. Thank you, guys. Good night, everybody.
All right, thanks. Bye.
Brian, I have group meeting tomorrow morning, right? Like for me.
Yeah, I sent a message. So let's meet on the other Zoom, and we can talk about what we're gonna do.
Okay.
Okay.